teaches papers on managerial finance, strategic analysis, financial modeling, and business forecasting, and many other. He is a dedicated teacher, astute researcher, corporate consultant, and a management trainer. His areas of interest are corporate finance, asset pricing, financial econometrics, and he is also a recipient of highly commended paper from Emerald. Sir has participated in various national and international conferences, delegations, seminars, and is actively contributing in the field of research. He has also been invited to various workshops as resource person and faculty development programs and management development programs. We are very thankful to Sir to take out time out of his very busy schedule and agree to be a resource person and share his valuable insights for this topic. I would now like Sir to start. Thank you so much, sir.
Thank you, Priyanka. Are we expecting some more students to join, or should we start the session?
Sir, we can start the session. Students will join. They are joining. There are going to be around 110 students. They will join in next 5 minutes or so. Sir, we can start.
Okay, so let's start for the day. The topic for today's discussion is time series data analysis. And let me start with a quotation belonging to the time series data analysis in particular, and okay, the various aspects of life in general. This quotation belongs to Albert Einstein, and it says, if you can't explain it simply, you don't understand it well enough. Okay? So things which are explained can be explained in a simple word, in simple lucid manner. Okay, that means, okay, probably the understanding of the concept, okay, is okay, probably more. So I will also in our session we'll try to get into this kind of an insight as to what is that okay, that simplicity, okay, with respect to the concept which are belonging to the time series, which is okay, is of importance to many researchers, because when we deal with these kinds of researches, okay, so invariably, okay, what generally happens is, okay, the meaning and understanding is lost in between. Okay, so if we try to talk about these things, okay, so then the simplicity, the understanding, the vitality, the point in question, okay, becomes of paramount importance to us. Okay, so let's begin with our journey on time series data analysis, and I'll try to take some of these concepts, okay, which are related to time series data analysis, and understand it, okay, in a more conceptually, okay, a clearer way, okay, in a conceptually more important and synthetic, okay, way of really looking at the data analysis. So let me, okay, begin with okay, a very crude definition of what exactly is the time series data. So what we generally understand by a time series data set, okay, we define a time series as something, okay, which is being measured over a period of time. So a time series is generally construed to be understood as that these are values of a variable y, which have been recorded at various points in time. So time point 1, time point 2, time point 3, so and so forth. So you have a time scale, okay, a timestamp has been there, and then you have a variable, okay, whose values are being recorded over time itself. This is how we understand by the time series. Okay, so this is our understanding of a time series. So anything which has been recorded over a period of time is referred as a time series data set. So record GDP of a country, okay, over a period of time. You record the okay, uh, interest rate, okay, over a period of time. You record the stock prices over a period of time. You record returns over a period of time, and so on and so forth. So there are multiple, okay, uh, variables, okay, which you can record it over a period of time. And the moment you have been recording any variable, any, okay, something of interest to you over a period of time, we are referring that as a time series. Okay, so time series deals with the data set which has been collected, ob observed, and recorded, okay, chronologically over a period of time. And then that makes a series as a time series data set. Okay, that's our definition of the time series. Okay, that's what we generally understand by that. Okay. However, okay, we will try to be shortly looking at that what how exactly we are defining, okay, time series in a data analytic, okay, perspective. So okay, but before that, okay, first question becomes that what is okay, unique about the time series? Why should we study time series, okay, in a slightly different context itself? Okay, doesn't, okay, our simple analysis, okay, which you use to conduct on a cross-sectional data set is sufficient enough to have analyze the data set which has been recorded over a period of time? So is there something peculiar about a time series which with which, okay, we need to be aware of, okay, and then use our data analysis techniques, okay, on that itself? So there is a okay, there is an okay, something okay, of an importance to us, okay, as a part of the time series data analysis. And how does the time series data analysis differ from that of a cross-sectional data analysis? So you have a cross-sectional data set and you have a time series data set, and okay, how do they differ, okay, and which makes us, okay, to study the time series data analysis in a slightly different context. First is it is in terms of, okay, conceptually the difference between the notion called population versus a sample. When we talk about in a cross-sectional data set, okay, something like okay, let's say in the same uh, okay, refresher course itself, okay, so what is the level of motivation of all the okay, participants of this particular refresher course itself? Okay, so it's a cross-sectional data set, so there are, okay, 100 odd number of participants, okay, and what are their level of motivation? So a simple cross-sectional data set. So here you do have, okay, a notion of the population versus sample. So as of now, okay, whosoever has been present, okay, if I may have a look, okay, so there are 42 participants who have been there, but there are more than 100 such okay, and participants enrolled for the program. So I have a sample of 42 such participants, okay, and I want to understand what is the level of participation, what is the level of motivation of all the 100 such participants to the program itself. So that's the concept of the population versus sample. Okay, so you have a notion of population and you have a notion of sample. Okay, in the context of time series, okay, these notions of population versus sample is, okay, slightly distorted, slightly different. Okay, so it's not in the same way wherein you do understand the population and the sample. Okay, but it's a slight, okay, a modification which has been there in the time series context. And whenever you try to analyze a data set which is a time series, okay, your notion of population versus sample is also been distorted accordingly. So there you have an analogous concept of process, stochastic process, and you have an analogous concept of realization. Okay, so there is a process concept, there is this realization concept. Okay, and these are the analogous to the population and the sample. Okay, in the context of time series and cross-sectional data sets. What are these? Okay, I will shortly be pondering some amount of time on that itself. Second important thing which is there with the time series data set is, so there is something of importance in the ordering of the data itself. So among the 42 participants which I've been having, so if I start with, somebody whose name start with A, B, C, and so on up to Z, or, alternatively, I start with somebody whose name start with Z, and then Y and X, and so on and so forth, and go up to A, or I take it any order M, N, O, P, and start anywhere from that itself. The ordering in which you have collected a data, you have used a data, or you have analyzed the data has no informational content for the cross-sectional data set. Okay, so in a cross-sectional data set, the ordering of a data, whether you have ordered the data in a descending order, whether in an ascending order, or in any particular order, which is based on your research design, has no relevance, no information to us. While in the context of time series data set, there is a chronological order. There's a natural order in the data set, which is based on time, which is what we are referring as a chronological data set. And this ordering, has information for you. Okay, so it's not that that if you would have picked up anything on the regression or on the kind of order in a cross-sectional data set, they may not be able to tell you anything about any more about the data set. Okay, but here this ordering of a data set will be telling you something more about it. Okay, whatever in nature. Okay, it might be positive or negative. For example, this ordering might result into the third issue, which is what we refer to as the serial correlation or autocorrelation problem. But even if it has been there or not, this ordering is simply has no relevance at all in the cross-sectional data set, and this ordering has a relevance for the time series data set. So you can't start with GDP for the year 2017, then you go down to GDP for the year 2015, and then you go to GDP for the year 2021, and so on. This ordering of the data set is important to us. So what we have, as far as the ordering of the data is concerned, which is a chronological in a time series context, it gives you some more amount of information which is for relevance to us. Then thirdly, there is a presence of serial correlation in the time series data set. In 99% cases, which wherein you analyze a data set which is serially correlated, there is a presence of serial correlation problem. So there's an autocorrelation or the serial correlation problem, which is being found in a time series data set. This serial correlation, it's hardly been there in a cross-sectional data. There could be some rare instances where the serial correlation can still be there, in one of the, let's say, snowball sampling version, there could be this serial correlation problem, but it's very rare in a cross-sectional data set. But in the context of time series data set, there is an existence of serial correlation problem in the time series data set. So invariably, but probably that could be what you could put up as your default setting, that if you are dealing with a time series data set, that there is a problem of autocorrelation in your data set. So you need to analyze it slightly differently. And if you ignore the problem of serial correlation, or what is also being referred as autocorrelation problem, then your estimates of the coefficients which you have arrived at are inefficient itself, which technically means that these estimates which you have arrived at, suppose you have run a regression, y is equal to alpha plus beta x1, and it is a time series data set, so it's based on subscript t plus the epsilon, the error term. So the estimate of alpha and beta which you have arrived at, they are inefficient if there is a problem of serial autocorrelation in your data set, which 99% cases of time series you will definitely be finding it. And if your estimates of alpha and beta, okay, they are uh, subject to a problem of serial autocorrelation, that means they are showing the property of inefficiency. That means these alpha and beta estimates are not at all useful for at least two things, okay, for your data analysis. Firstly, these are not useful for conducting any sort of hypothesis testing. So if you want to conduct any hypothesis test, whether alpha is equal to 0 or not, okay, or alpha is equal to some, okay, some constant, okay, some 50 or something, okay, that you can't test it, okay, whether beta is statistically significantly different from 0 or not, okay, those hypothesis testing you cannot use if there is a problem of autocorrelation, okay, which in other word means that there is an inefficiency in your estimate. The second thing, okay, which makes your these data set, okay, not at all useful is, okay, for construction of a confidence interval. Okay, so you can't construct any confidence interval. So suppose your estimated figures are 100, okay, so what is the lower limit, what is the upper limit, okay, will it be from 95 to 105, or will it be from 92 to 108? Okay, what is the, okay, confidence, the upper limit and the lower limit of, again, okay, your data set is not at all being useful, okay, so you need to be careful with respect to the time series data set. If you have been trying to analyze a data set, okay, which is a time series data set, okay, you will be finding this kind of a problem. So you need to be aware of, okay, at least some of these problems which you might run into. Another, okay, thing which you should also be really, okay, concerned about, okay, while analyzing a time series data set, okay, is the issue of the stationarity as well, okay. So I'll come back to the problem of stationarity too, okay, in this okay, context itself. So you do not have a cross sectional okay, data set, okay, subject to a issue of stationarity, but in a time series data set, the stationarity is also you need to uphold as well, okay? So there are a few things, okay, which you really need to, okay, keep in mind. And when you, okay, if you are trying to analyze your data set, which is a time series data set, and that doesn't, okay, uh, go with okay, some of these understanding which you have special understanding for a time series data set, okay, then, okay, there could be issues in your data analysis and interpretation as well. Besides these issues, okay, the toolbox which the data analyst has, okay, is same as that of a cross sectional. So if you have enough understanding of your cross sectional data set, okay, the statistical tool, the way of analyzing, okay, conducting and hypothesis testing and things like that itself, okay, then, okay, same thing can also be applied to time series as well. So there's no problem, okay, so that remains the same, okay. So the way you have analyzing your data set, okay, otherwise as well, is also been applicable for a time series data set. So you need not be worrying about that aspect itself, okay. So only few things, okay, countably few things is what you really need to be, okay, aware of, okay, really need to be taking care of, okay, when you talk about a time series data analysis, okay. So in a brief recap itself, okay, so first thing is, okay, the notion of population versus sample, okay, that understanding is getting altered, okay, in a time series context. That's the first thing. Secondly, okay, you can't, okay, uh, uh, have a, okay, a power to negotiation with as far as the ordering of a data is concerned, okay. So it has to be from 2018 has to fall after 2017 only, 2017 has to fall after 2016, okay. So there is this natural ordering of the data set, okay, which is in a chronological context, is, okay, is something which you really need to be, okay, careful of. And this ordering of a data set, okay, at times gives rise to a problem of the serial correlations, okay. Almost 99% time series is which we generally deal with, okay, mostly economic and the financial time series, they have this kind of a problem, which is, okay, the issue of, okay, the presence of autocorrelation problem. Okay? So today's data set is related to, okay, at least in a, okay, assumption which we run a regression, okay, that the error term for today is related to the previous error terms. Okay, so you really need to be taking note of these things, okay, when you try to analyze a data set times. Otherwise, okay, there's no problem. Whatever you have been using it for a cross-sectional data set is also been applicable, is also been useful for a time series data set as well. Okay, okay, so okay, so when we talk about these kinds of the issues itself, so whenever you run a regression model, which is one of the most versatile tool available to a data analyst to conduct many type of analysis itself, and that happens to be a regression model itself. Okay, so whether it's a comparison of mean, you can again run a regression. Whether you want to classify something into different categories itself, again you can use regression itself. So regression is a very versatile tool. Okay, so besides talking about whether it can relate one uh, variable to another variable, besides that, okay, it has a lot of applicability. So it's a one of the okay, uh, you can say a highly useful tool for the data analyst. But whenever you run a regression, a typical regression which you go for it, wherein you have a dependent variable and you have independent variables, at the back of running a regression, there are a couple of assumptions which are being made. So your standard econometric text talks about 10 such assumptions which are at the back of running a regression analysis itself. Okay, so whenever you run a regression, at the back of it, particularly when you've been talking about multiple regression, then there are 10 assumptions which are at the back. Okay, so whether you are conscious about it, whether you know about it, whether or you don't, you have already made those 10 assumptions at the back of it. And when you go for analyzing your data set, these assumptions are been there. Okay, and when you try to rush to interpret your data set, these assumptions, the validity of these assumptions are been important. Okay, so unless these assumptions are being validated, you should not be rushing to interpret your regression results itself. So these are the 10 assumptions. Okay, and I'm not focusing on those 10 assumptions. Okay, that's not what is the mandate for today. Okay, but yes, there are these 10 assumptions which are at the back of a regression model itself. Okay, the one which I've been focusing on, that this assumption is an assumption which is typically not being validated in a time series data set. Okay, so in a cross-sectional data set, yes, this is also true that this one or many other assumptions may not be really been able to be upheld when you go in for a data analysis, but this is such assumptions which are typically being violated in a time series context. Okay, and that's what I was talking about in the previous slide as well. Okay, this is what is I'm also referring as the serial correlations as well. Okay, so you have an assumption of that error term mean is being 0. You have assumption of homoscedasticity, that the variance of the conditional variance of the error term is a constant number. You have a assumption regarding multicollinearity, where the two independent variables are highly related to each other. Then you have an assumption of exogeneity, where your one of the independent variable is related to the error term. And you have an assumption of normality. And then some assumption relating to specification parameters, the sufficiency of the observations, and sufficiency of the variations itself. So there are 10 assumptions which are at the back of running a regression model. But out of these 10 assumptions, the assumption which are typically being violated in a time series data set is the assumption of no autocorrelation, where error term at two different points in time, this is generally measured on a time series data set, is not equal to 0. So there is some ordering which is some impact which is been exerted by the error terms for one time period to the error terms to another time period. Today's stock price returns is affected by yesterday's stock price returns. Today's exchange rate is affected by the yesterday's exchange rate. today's FII's investment into Indian market is affected by yesterday's FII investments. Okay, today's GDP is affected by the quarter's GDP itself. Okay, and so on and so forth. So there is a high amount of correlation which has been existing, in a typical economic and financial time series. Okay, in a more of a simulated series, okay, you might find a complete absence of this autocorrelation, but in most of the economic series, that's why I was saying almost 99% cases, okay, you'll be finding that the economic and the financial variable of your interest is really being affected by the previous years or previous days, okay, or previous time periods, okay, observations itself. If that happens, okay, you are really having this issue, okay. So otherwise, okay, if this has not been there, okay, you are good to go. You can run a regression, you can make an interpretation, use a data analysis, okay, for your interpretation, and so on and so forth. Okay, so that's what you can proceed further. Okay, so there is no problem in that case. Okay, but typically for a time series data set, okay, the assumption number 7 listed here in the slide is the one which has been generally violated. Okay, so you need to be really focused on this kind of an this assumption itself. Okay, the if the validity of this assumption, if this assumption is not been validated, okay, results into inefficient estimate. Okay, and the implication of having an inefficient estimate I've already talked about earlier. Okay, okay, so this is something, okay, which you really need to be really looking at in this context. Okay, now coming to all those three points, okay, one by one itself. Okay, so this one, okay, I've had an initial discussion. Okay, this one I have already talked about in terms of the implications. Okay, in the next slide. Okay, let me now focus on this one. Okay, and coming back to the assumption, the definition of a time series, which is a more concrete way of to be used for a data analysis purposes itself. Okay. Okay, so let me now define what exactly is your time series in a proper way itself. Okay, so what is a time series? Okay, which we use for the purpose of data analysis. It's of course for the purpose of data recording and collection. Okay, and then using it for your interpretation purposes. Okay, we are referring to that. Okay, obviously that same thing is a variable of interest observed or recorded over a period of time. Now let us use it, okay, from the context of sample versus population itself. Okay, so when you try to define what is the process in the context of time series, what does that exactly mean? Okay, so so there are three things, okay, which we really need to understand. Okay, so one is a variable. Okay, the second one is a random variable. The third one is a stochastic process. Okay, so let's first focus on these three concepts. Okay, so what is a variable? A variable is a quantity which is of interest to you, okay, which vary from the one respondent to another respondent. Okay. That's how we can in a simple word define the term the variable itself. So some things of your interest, some quantity of your interest, okay, which can vary from one respondent to another respondent. Okay, if it does not vary, okay, then probably that's really not a variable. Okay, so what is the level of motivation of all the participants of this refresher course? Okay, will be a variable which will differ from one respondent to another respondent. What is the age and height of or the respondent? Again, that will be differing from one respondent to another respondent itself. Okay, but if I ask you, each one of you, okay, each one of you draw a circle of a radius, okay, of whatever radius you want to define. Okay, measure the circumference of the circle and divide it by the diameter of the circle. Okay, now that will be something which will not differ, which should not be differing it from one respondent to another respondent, because that should be a value of pi. Okay, and that must not be differing, okay, accordingly. So that's not really a variable, but something of variable is quantity of interest which has been varying over it, from one respondent to another respondent. Okay, then the second thing is the random variable. What is a random variable? Okay, this is a variable, okay, something which can differ from one respondent to another respondent, but this is the outcome of a random experiment. Okay, so one respondent, okay, coin, okay, takes a toss of a coin itself, head or tail. Okay, another respondent takes, okay, another, okay, coin tossing, okay, exercise itself, comes up with a tail or a head itself. Okay, so for each respondent there is a randomness which has been, okay, at the back of it. Okay, so yes, okay, respondent wise, okay, there's a difference. The variable of interest is differing from one respondent to another respondent, but it's coming up out of a random experiment. And what is my random experiment here? It is a tossing of a coin itself. Okay, so you can have your random experiment, which is could be coin tossing. This could be a throw of a dice. This could be a pack of cards of 52. Okay, this could be, okay, some Chaucer dices. Okay, which might be having 8 faces itself. Okay, and okay, in a cuboid version. Okay, or okay, anything which could relate to a normal distribution from minus infinity to plus infinity itself. So there could be anything, okay, of this random experiment, okay, or whatever in nature. Okay, I'm not defining the nature of the random experiment, but the only thing which I've been just trying to relate here is that it is an outcome of a random experiment. Okay, so if a variable is being arrived at, which is an output of a random variable, that variable is what you can call it as the random variable. Okay, so now there is a third thing, which is a stochastic process. Okay, so when you have a random variable, okay, which we have been measuring. Okay, so I have a variable, then I have a random variable. If I've been observing a random variable over a period of time, okay, then that is referred as a stochastic process. Okay, so I repeat, okay, when I've been measuring a random variable over a period of time, and that has been referred as a stochastic process. Okay, so if I ask you, okay, all of you, okay, to each one of you, okay, take a dice and roll a dice, get a value from 1 to 6, okay, at the same point in time. Okay, so right now, okay, as of now, which is what is the time? Okay, so 5 o'clock. Okay, 5:53, okay, p.m. Everyone, each one of you, throw a dice, get a value from 1 to 6. Okay, that's not what has been referred as a stochastic process. Okay, so I will be definitely been getting, okay, how many? There are 59 such participants. Okay, there are 59 participants, each giving me a number between 1 to 6. Okay, at 5 o'clock, okay, 5 h to 53. Okay, that's not what has been referring as the stochastic process. Okay, but yes, it is a variable. Okay, it can have a value between 1 to 6. It's a random variable. It is an outcome of a random experiment. But okay, is it a stochastic process? Okay, no, we are not observing it over a period of time. Okay, but if I ask you, one of you, okay, to roll a dice, okay, get a value from 1 to 6 and record it, okay, every minute itself. Okay, so 5:53, 5:54, 5:55, 5:56, okay, 5:57, every minute. Okay, so I'm having a time dimension. Okay, every minute what you do is, okay, you roll a dice, get the value and just record it over time itself. Okay, so when it was 5:53, you get the, okay, value as 5, and for 5:54 you get the value 1, when it is 5:55 you get the value 3, okay, and so on and so forth. Okay, so then I'm been experiencing and observing a random variable over a period of time, and that is what is referred as a stochastic process. Okay, so I have something which is a stochastic process. It's a random variable which has been observed over a period of time itself. Okay, so stochastic process has two dimensions. Okay, so dimension number one is the random experiment. Okay, for example, in this case it was a, okay, rolling of a dice itself. Okay, in the case of a coin toss, tossing example, okay, the random experiment will be, okay, tossing of a coin or taking a card out of the pack of 52 cards. Okay, or okay, reading the number on Chaucer dices. Okay, or so on and so forth. Okay, so you can have, okay, a various okay, nature of the random experiment. Okay, that's one aspect. And the second aspect is that of time dimensions as well. So you have both the dimensions, both the aspect for a stochastic process. Okay, so it has, okay, both the aspects, okay, time dimension as well as the random experiment itself. Okay, so you have a probability space, will also be the time itself. Time could be discrete, okay, time could be continuous as well, okay, but it has both the aspects relating to that. Okay, so there's a time dimension, and then there is the random experiment, okay, dimension as well, okay, which is the outcome of an event itself. So, so how can you have, okay, okay, observations recorded over time itself? So, what we could do is, okay, in this particular example, let me just take it another Excel itself. Okay, so let me just take. So what I'm doing is, okay, I'm just taking the various time points. Okay, so I have a time dimension to it. Okay, so T1, T2, third, fourth, fifth, sixth, seventh, eighth, ninth, okay, 10th. So these are the different time points. Okay, maybe different okay, minutes. Okay, or hours, or okay, whatever time period for which you have been defined. Okay, second one is I just want to get some rolling of a dice itself. Okay, so for the first minute, okay, I rolled a dice and recorded an observations here. Okay, so I'm just taking some of these data. Let's see. Let me just take a okay. Okay, so suppose I rolled a dice and I got the value 6, okay, on the first minute itself. Then again, I rolled a dice for the second minute, I got the value which is 5. I rolled a dice, okay, for the third minute, I get the value 1, and so on and so forth. So these are the different, okay, data points which I have obtained, okay, from a rolling of a dice itself. So let me just plot it, get some that. Okay, so these are my values which I have obtained. Okay, so out of the 10 minutes interval, okay, I rolled a dice and I got 2, 5, 1, 2, 1, 6, 1, 1, 6, 6. Okay, that's one such, okay, observations which I have obtained. Okay, and you can have multiple such, okay, paths. Okay, this is something which I have obtained. Okay, but may not necessarily be by, okay, each one of you. Okay, so this could have been something like this could have been something like this. Okay, so there is this natural, okay, different paths which, okay, which you can have had, okay, over this 10 minutes interval. So for next 10 minutes you roll the dice, you taken out, okay, the number on the dice itself, okay, and you have simply put up, okay, across the timeline itself. Okay, so their possibilities are, okay, for each one of them, okay, the possibilities are so many, but here, okay, you are only showing it out of the 6 different, okay, possibilities only. Okay, so what I have here is, okay, I could have obtained, okay, rather on the first, okay, I could have obtained 1, 2, 3, 4, 5, 6. Okay, these are the different possibility, but what I have obtained is only 1. Okay, even for second as well, okay, I obtained the 5, but I could have obtained, okay, any out of these 6 itself. Okay, for third as well, I could have obtained, okay, out of the 6 different possibilities, I obtained 1. Okay, for fourth one as well, I obtained 3, but okay, these are the different, okay, possibilities which you could have had, okay, in this case itself. So if I refresh my sheets, okay, I have obtained something like that itself. Okay, so every time point, okay, there are 6 different possibilities which are been there. Okay, but I've obtained only one of these 6 different possibilities itself. Okay, now what is okay, if it is a rolling of a dice, and we know that, okay, I can get 1, 2, 3, 4, 5, 6, and the probability of each one of them which can be obtained is 1/6 only. Okay, so if you take out, okay, what kind of distribution which you have been having, okay, from 1, 2, 3, 4, 5 and 6, okay, each having the same probability, which is 1/6 of the probability. Okay, this kind of a distribution is what we refer as the uniform distribution, because each have a uniform probability. In this case, it's a 1/6 itself, okay, of obtaining your observations here itself. Okay, so for each time point, okay, there is this uniform distribution, okay, having showing you the same probability itself. Okay, so this is what I have been having, okay, as a part of my stochastic process. Okay, so every observation is obtained randomly, okay, and they follows a random okay, a probability distribution, which is in this case for simplicity purpose taken as the uniform distribution. When you try to analyze the data set, when you try to analyze the time series, you generally make an assumption that you did have obtained the observation in hand, and they are coming from generally the normal distribution. So generally, okay, you make this kind of an assumption that there's a normal distribution which has been followed. Okay, so if I go back to the slide itself, okay, so this is what I've been having. So every okay, point which I've been having, this is t equal to 0, time equal to 1, time equal to 2, okay, time equal to 3, time equal to 4. Okay, so you are having, let's say, 5 o'clock, and this is 5:01, okay, 5:02, 5:03, 5:04. Okay, so this is the time point at which you have been okay, just getting, okay, one random value, and it follows a normal distribution. Okay, so that's a typical feature of a normal distribution. Okay, some bell-shaped curve. Okay, you need to be really looking at in a okay, uh, with, okay, okay, 90-degree rotation, okay, towards your left itself. So it can have any observation from -infinity to +infinity with a certain mean which is you have been having, and okay, it follows a distribution which is a normal distribution itself. Okay, so these are, okay, the various possibilities which you have been having, okay, at 5 o'clock, and you are getting just one of these several different possible, okay, values itself. Okay, to really come up with what is your, okay, time series data set. Okay, so you have, okay, something like for this time equal to 0, okay, you obtain this one, suppose. Okay, this is my assumption. For second, okay, time point, you obtain the next one. Okay, this is what you have observed. This is for the third time point, this is for the fourth time point, this is for the fifth time point. Okay, so you have obtained, okay, some observations over time, and when you try to connect them, okay, is what you are calling them as a time series. This is what is your time series. Okay, now remember, this is one of the several different possibilities itself. Okay, so if you have connected, okay, these observation, you have obtained this one, but okay, remember, okay, there could have been a possibility that this would have been your first observation, this is your second observation, this is third observation, fourth observation, and fifth observation. So you could have got an alternative path as well, something like this one. Okay, or you could have also obtained something this, and this as well. Okay, so no change at all. Okay, but that's also one more time series which you might have obtained as well. Okay, you could have had, okay, another, okay, time series itself, okay, wherein again there is a -infinity to +infinity. Okay, so you can get some random variable varying from -infinity to +infinity. following some normal distribution itself, and you obtained one of the data points on these 5 different time points. So this one, and this one. You try to connect them, and you have got another time series itself. Okay. Quite looks quite similar to the first one as well. Okay. So even for first one, okay, you are having this time series. For second one, okay, you are having this, sorry, this time series itself. Okay. But yes, okay, there is a difference between, okay, these different time series itself. Okay. So here you can, if you just have a look at it, because I will be coming back to it once again itself. Okay. So here, if you observe the nature of the distribution here, okay, what you can make out is that all these different distributions, so if you call this as, this is the distribution 1, this is the distribution 2, this is the distribution 2, 3, this is the distribution 4, and this is the distribution 5. Okay. What you could make out in this case, all these distributions are identical distribution. Okay. So their means are the same, their variances, okay, is also the same as well. Okay. So they are almost identical to each other. Okay. But in this case, okay, the you can observe the mean is not the same. It's constantly been, okay. You can just take a scale here. The mean here is this one. The mean here is slightly higher. This is third mean. This is the fourth mean. This is the fifth mean. The mean is escalating, okay, over time itself. So it's not the same distribution. Okay, the variances looks the same, but the means are not the same. Okay, while in this case as well, okay, the means looks the same. Okay, probably all of them are have showing you the same mean value. Okay, distribution first, second, third, fourth. Okay, they are having same mean value, but the variance here is lower, but the variance here is higher. Okay, so I'm giving an example where mean and variances both are same. That was the case number 1. The case number 2, where mean is not the same, but the variance is the same. That was case number 2. And this is case number 3, where mean is the same, but the variance is not the same. Okay. So that's a case number 3 itself. But all of them are time series data set, and all of them are stochastic processes itself. Okay. So we are not making any segregation. The only conditions to define something as a stochastic process is it has to come up with it with a, okay, from a random experiment itself, okay, and which you have been recording it over a period of time itself. Okay, so here again, this is also a stochastic process itself. Okay, so we are not changing anything on that. Okay, and okay, you could have obtained these different observations for different time points itself. Okay, now if you try to connect them, okay, and this is what you can call them as your time series data set. Okay, so the important thing is that, okay, you only realize one realization out of the several different possible ranges itself. Okay, so in our controlled experiment, which was the rolling of a dice. Okay, so when you roll the dice, you get the values. Okay, so I'm assuming, okay, that I rolled a dice in the first place, I rolled a dice in the second place, I rolled a dice in the third place, okay, and dice rolling in the fourth, and dice rolling in the fifth as well. Okay, so same experiment is what I've been repeating it for on different points. Okay, now it's not necessarily that it will be a same experiment itself. Okay, but I'll take that case later. But I'm rolling a dice and I am just recording the observation itself. Okay, so I obtained 3. Okay, let's take 4, 2, okay, 4, 5, okay, 2. This could have been, okay, one such, okay, path which you could have followed in a particular case, okay, when you are rolling a dice over time itself. But this is not the only path. Okay, there could have been something like this. In the first, okay, time point itself, you would have obtained 1. Okay, in the second, this you would have obtained 3. Okay, and so on and so forth. So there could have been some alternative path, but okay, uh, when you observe a time series, okay, typically you observe only one realization out of several possible realizations itself. And in this case, okay, because you are dealing with a normal distribution, okay, where the ranges are minus infinity to plus infinity, Okay, so there are infinite possibilities which have been there, but you only observe one of those infinite different possibilities itself. Okay, so time series deals with, okay, the one of these realization out of the different possible realizations which you can have had, okay, if you have really know the nature of the experiment itself. Okay, so all these realizations, okay, are some way or the other, okay, telling you about the underlying nature of the stochastic process itself. That means a random experiment which has been observed over time itself. Okay, so now formally defining what exactly is a time series. Okay, so we crudely define time series. The time series is something which has been, okay, is a value of interest recorded over a period of time chronologically. Okay, this is how you used to define a time series. Okay, now a more data analytic perspective of really defining what exactly is the time series. A time series is realization of a stochastic process. So you have a stochastic process, okay, and one of the realization of that stochastic process is what is referred as the time series. Okay, so every realized observation, okay, of a stochastic process is understood as a time series. Time series, okay, now formally defined in a more data analytics way, is that it is one of the realization of several possible different, okay, manifestation of the stochastic process itself. Okay, so you have a stochastic process and you have a realization. Okay, so the process is what is analogous to a population, and the realization is what is been referred as your sample. Okay, so in a cross-sectional setup, what you try to do is, okay, you use a sample information to make a comment about what the behavior of the population itself. So in the context of time series, okay, you try to study the realization, and remember this is one of the several possible realizations we could have had. Okay, so you look at the realization and you try to make a comment of the underlying stochastic process itself. Okay, so you try to comment on what is the basic nature of the random experiment which has been generating these realization itself. Okay, so that's the analogous concept which you have a time series. So in the time series, okay, we typically do not, okay, really use these words of sample and population. But yes, of course, okay, to give you an understanding, okay, and to just relate it, because, okay, time series is generally being taught with after the cross-sectional toolbox has been talked about. So you are already familiar with population and realization. Okay, so we also borrow those concepts and apply it. Okay, now that's not really the correct way of doing it. Okay, but yes, okay, to really assist your understanding, okay, we apply this concept of population sample. But these concept of population and sample per se, okay, they do not exist in a time series. In time series context, okay, we really comment upon the stochastic process and the realization. Okay, and so we try to make a comment on what is the nature of the process from the realization, okay, of the process itself. Okay, which is your analogous to the sample and the time series context. Okay, now okay, though I will be coming back to that issue itself. Okay, and that's why I postponed our discussion a bit. Okay, because these are the three okay things which I'm just, okay, come back again and again itself. Okay, so remember this, what is the nature of this stochastic process itself. Okay, so here, okay, the all these distributions, okay, and we call them as conditional distribution. Okay, so these are distribution, obviously here in this case, okay, including zero. So there are five such distributions are there. There are five conditional distributions. Okay, and the nature of these distribution is that they are exactly the same. Okay, same mean. Okay, for first, second, third, and all the fifth itself, same variances. Okay, so that was a case number one which I was talking about. Now this is a case number two, okay, where these five conditional distribution, their means are, okay, shifting upward itself. Okay, so their means were not same. Okay, but the variance was the same. Okay, so variance same, but means were not the same itself. Okay, so we put a dot, okay, to refer to a variability, and a bar for the constancy itself. Okay, so this is case number 2, and you have case number 3. Okay, where you have means is the same, but the variance is not the same. It has actually been changing. Okay, so means are the same. Conditional means of all these distributions are the same, but variance is not the same. Okay, it's actually been changing itself. Okay? So that's case number 3. And yes, of course, you can have case number 4 where the mean is also changing, the variance is also being changing. Let me give an example itself. Okay, so what you do is, okay, at 6 o'clock, okay, you rolled a coin, you tossed a coin, and you obtain the observation. At 6:01, okay, what you did, okay, you rolled a dice. Okay, at 6:02, or what you did was, okay, you rolled a Chaucer dice with 8 faces. Okay, then at 6:03, okay, what you did was, okay, you rolled a pack of 52 cards, and so on and so forth. Okay, obviously, for each of these random experiment, mean is not the same. Okay, the variance is not the same. Okay, but it is still called a stochastic process. It is still called, okay, the observation obtained will still be referred as realizations itself. Okay, so it is still a time series. Okay, now it's entirely of a different, okay, plane itself, that probably what you do with these kinds of time series. Okay, what kind of problems you might be running into when you try to analyze this kind of a time series, that's a different thing, but it is a time series. Okay, and we are still talking about, okay, the random experiment and the stochastic process itself. Okay, so there's no problem in that case. Okay, so there's a forecasting problem lying in these kinds of time series, but okay, these are time series itself. Okay, so there's no issue as far as the basic definition of the term time series is concerned. Okay, now bringing along, okay, one more point itself. Okay, and that's, I'll connect it, okay, afterwards as well. Okay, is the issue of the stationarity itself. Okay, so I'll come back to this issue one more time. So there's something called as a stationarity. Okay, now stationarity is again a concept which is related to the time series data set, and stationarity is, okay, is not been talked about, okay, for a cross-sectional setup. Okay, so if you have a data which is a cross-sectional data, okay, you are really not been worrying about the concept of stationarity. But when you do have, okay, time series data set, okay, you need to be worrying about the concept of stationarity. Now, what does stationarity means? Okay, so stationarity in its weak form, okay, so there are multiple variant of the stationarity itself, but as generally understood and applied, okay, in the data analysis context itself. Okay, so generally stationarity, okay, as applied for the data analysis purposes, okay, implies that your mean should be constant and the variance should also be constant. Okay, and again, covariance should also be not a function of the time lag as well. Okay, that's another third condition attached to it. Okay, but crudely, what does stationarity means? That the mean and the variances should be constant as well. Okay, so for example, for this first one, where you have these 5 conditional distributions, okay, the mean of each of these conditional distribution is the same. Okay, the variance of each of these conditional distribution is the same. Okay, so this kind of a time series is a stationary time series itself. Okay, let's take the case number 2. Okay, here the mean was is not the same. It was constantly going upward itself. Okay, and if you apply the context of stationarity itself, with the mean should be constant and the variance should be constant. Okay, so that is not getting fulfilled here. So the variance is the constant, but the mean is ever shifting itself, so that's also not a stationary time series. Okay, let's again go for the third one as well. Here again, okay, you are finding it, okay, that the variances is not constant. Okay, variances is actually been changing, and the means were remaining constant as well. Okay, so this kind of a time series is also not a stationary time series. Okay, however, there are, okay, other condition attached to it, but in a crude way you can also understand, okay, the basic nature of the distribution, and commenting upon whether the process is a stationary process or not. Okay, so you also need to be having, okay, observing time series, okay, in this context as well. That's why I took these three examples where the mean variances are the same, okay. And the second example, the mean was not the same, but variances were the same. And the third example, this one, okay, this is what I'm calling as a third example, where the mean is the same. Each of these distribution are having the same mean, okay, but their variances, okay, is not the same. So this is, okay, very low, okay. You can look at the range as well, and okay, this is typically very high. Okay, so you can find that the variances is again not the constant itself. Okay, so this is not a stationary process as well. Okay, but both of them, okay, or all of these are still a random experiment. All of these are stochastic processes, and all of these are really, okay, manifesting at least one realization which you have been recording. These stars are what is, okay, one of the several possible realizations, and these are all time series, and this is how, okay, we are going ahead, okay, in terms of okay, defining the time series in this particular context itself. Okay, that's the first aspect. Okay, so the idea here for this particular session was to make you aware that how does a time series data analysis differs from that of a cross-sectional data analysis, okay, typically, and what are the things, okay, which are in difference with what is a cross-sectional, okay, data analysis, and okay, what you need to be really, okay, careful, okay, and what you should really be, okay, concerned about when you have been trying to analyze the time series data set. Okay, so the first thing, okay, again as a recap, is that, okay, the first thing which you should be really taking note, okay, so the notion of population and sample, okay, is converted in a time series context as a process and the realization. Okay, so process is your population, equivalent of a population, and realization is the equivalent of your sample. That's the first thing, okay, so that you should be keeping in mind. Secondly, okay, the ordering of the time, okay, is important. So this was t equal to 0, t equal to 1, t equal to 2, and so on and so forth. Okay, so you can't take this distribution, okay, and take it back, and this distribution you take it forward. You can't do it. Okay, so there, this ordering is important, which is a chronological ordering. Okay, that's the second aspect. The third aspect, which you typically find, that this observation is generally related to the previous observation. This observation is generally related to previous observations. Okay, there is a high amount of correlation which has been happening here. Okay, so this is what is your serial correlation problem, okay, which is typically there in your data set itself. Okay, for example, if I continue with that same example of a rolling of a dice, okay, so you obtain one of, okay, 1 to 6, okay, from the first observation, 1 to 6 from the second time point when you roll the dice. But you know, when you roll a dice second time, it has nothing to do what was the outcome of rolling of a dice, okay, the previous minute. So when on 6 o'clock, okay, when 6 o'clock, when you roll the dice, you obtain some number here. When 601, okay, when you again roll the dice and you obtain another number here, but you know that this number has nothing to do, theoretically has nothing to do with the previous number. So in the last minute, what was the outcome of the rolling of a dice, and this minute, what is the outcome of a rolling of a dice? There is no connect. Okay, that's what theoretically should have been. Okay, so then there is no problem of no serial correlation problem, theoretically, in the case of rolling of a dice. But typically, when you talk about GDP, foreign exchange, inflation, okay, interest rates, okay, unemployment data set, stock prices, okay, asset prices, valuations, okay, and so on and so forth. The typical series is which you take up, okay, this theoretical, okay, feature of no connect between the two observation is generally not been there, and hence as a result of which there is a serial correlation issue, and that results into inefficient estimates. Okay, and the culmination of inefficient estimate is that these are useless for testing of hypothesis as well as, okay, construction of a confidence interval. Okay, for both these purposes, these are simply useless. So you need to rectify them. Okay, how you rectify them, okay, that's another, okay, how to detect them, how to go about it, how to rectify them. Okay, that's another topic for discussion itself. Okay, but you really need to be concerned about the presence of serial autocorrelation problem, the time series data set. Okay. Okay, so let me take a few more query. Okay, so stochastic means random. Okay, stochastic. Somebody asked what is the difference between stochastic and random. Okay, so stochastic, once again, I define it. Stochastic. Okay, yes. Okay, but some of you might have when you studied sampling. Okay, you also call it as a stochastic sampling, as same as random sampling. Okay, so that way, okay, you are fine. But okay, when we are using the stochastic word in a very much okay contextualize itself. So stochastic is random plus a time dimension. Okay, so it's not one and the same thing. It's slightly more than random. Okay, so stochastic process is a random plus a time dimension attached to it. Okay, so you cannot literally be okay random, but yes, okay, quite often for various authors they use the word stochastic and random interchangeably. Okay. Okay, another issue is that of a stationarity. Okay, so stationarity. Okay, I'll come back as well to the stationarity issue as well. Okay, so wherein the uh, attributes of these conditional distributions which we are having here. Okay, so if these attributes of these conditional distributions, okay, if they are maintained, they are exactly the same, then the time series will be called as stationary. If these attributes, okay, they are not same, okay, then the time series is referred as non-stationary. Okay. So if I take that example of a rolling of a dice, if every time it's a rolling of a dice, I'm not changing anything on that, it's a stationary process. Okay, but okay, I gave an example that it was firstly for 4 minutes it was rolling of a dice. For next 4 minutes it was a pack of 52 cards. For next 4 minutes it was a okay tossing of a coin. Then that's not a stationary process, that's a non-stationary process. Okay, so the attributes of the distribution. Okay, what do I mean by the attributes of the distribution? Mean, median, okay, your skewness, kurtoses, okay, and so on and so forth. Probably you can extend it to any level itself, but generally we are more concerned about mean and the variances, first and the second moment itself. So if these attributes remains the same, okay, then the process is called a stationary process. And if these attributes are not the same, okay, then the process is referred as non-stationary process itself. Okay. So that's the first aspect of the time series itself. Okay, so still any question, any doubt to anyone? Okay, that they can put up in the chat box itself. Any issues, any question to anyone? Now this is something which is quite basic to time series. So when you have been working with the time series, okay, uh, be sure about okay this kind of aspects of time series. Rest of it okay is the
So,
same.
sorry to disturb, sir. Can we say that all financial data are non-stationary then?
Most of the data set with which you generally work, okay, you invariably be finding is a non-stationary. Okay, that's why you generally
Okay, sir.
work with okay their transform data. So you don't work with the inflation, you don't forecast a CPI. What you forecast is a rate of inflation. Okay, so you don't forecast the GDP. What you forecast is a growth rate in GDP. Okay, so that's why okay you will mostly be working on okay so you don't work on the money supply data. You talk about what is the growth in the money supply itself. So you don't work on time series, so sorry, non-stationary data. GDP is typically non-stationary. The inflation indices are non-stationary. I'm not talking about inflation rate, I'm talking about inflation index, CPI or WPI. Okay, this is generally the
But
non-stationary.
sir, if we talk about the change in that particular variable, for example, change in market price of the shares, then can we say that it could be stationary?
Yes, that could be stationary. Typically, the series is okay, but you work with is non-stationary, but okay, their transformations, okay. And what do I mean by transformation is these rate of change. So the
Okay.
inflation rate is typically stationary. the returns on the stock prices, they are typically stationary. So stock prices are non-stationary, but returns on the stock, okay, they are typically stationary series, okay, and so on. Okay, so GDP is non-stationary, but the rate of change, growth rate in GDP, that's typically okay, stationary. I'm not saying okay in all the cases, but typically. So most of your economic and financial variable, most of your variable, okay, I'm still not putting a 100% cap on that, okay, but at least okay 90 to 95%, okay, the variable of your interest is typically non-stationary, and you always work on their transformation itself, okay. So your sales is non-stationary, your assets, total assets, okay, total fixed assets is typically non-stationary, but when you compute okay turnover ratio, asset turnover ratio, typically that ratio might become a stationary itself, okay. So you generally work on those transformed series, and you do not work on okay the level series. So you don't work on sales, you don't work on the assets, you work on the asset turnover ratio, which is sales divided by the total asset. So you don't work on GDP, you don't work on money supply, but you work on okay growth rate in GDP or growth in money supply itself, okay. So your growth numbers, which are transformed numbers, they are typically stationary, while your okay GDP numbers or money supply numbers, they are typically non-stationary itself. Yeah. Any other query to anyone?
Sir, I have a question. I wanted to know, like the absolute data, which is non-stationary, if we calculate the Z scores of those series, can we say that it is converted into stationary form with the Z scores of the data? And if you work on the Z scores?
Then I also need to look at it, probably how you are converting them into okay the Z scoring itself. Okay, if it is
In
unconditional.
SPSS, there is a provision like we get the Z score of the data series. So if you convert all the data series into their respective Z scores, and then we work on that. So can we call it as stationary data?
Again, okay, to an extent, okay, I really can't comment because okay, this conversion of a Z score, which is taking the variable, deducting a mean from that, and dividing it by the standard deviation, which is typically the way in which you compute your Z scores itself, okay, that can contain okay your mean and variances in a range, okay. So of the Z score, the mean will always be equal to 0, and the variance of the Z converted okay number will also be always equal to 1. Okay. So now you have made a series, okay, which is okay, but again, that conversion is across the entire across the data set itself. But when I've been talking about the stationarity aspect, okay, when I've been talking about stationarity aspect, it's not that okay. So if these are all X variable and I converted them into their Z scores, okay, corresponding that itself. But what has happened, okay? So rather than from minus infinity to plus infinity, so nature of this normal distribution which you have been following here, okay, had a mean which was 50, and okay, this conditional distribution, okay, and now has okay the standard deviation was okay 10, okay. This was the nature. Now that was belonging to the series X. Now you have a series Z, okay, that it has a mean which is 0 and the standard deviation is 1. Okay, that you have already made and okay transform the series itself. But can that make this series stationary? Okay, will still not be okay right way of looking at the question itself, because even if you have okay, taken the spectrum out and made the mean to fall equal to 0 and the standard deviation okay to fall to be equal to 1, okay, so you have made at least okay that the things will now be falling in a okay contained spectrum, not as much high as much low, okay. But what you have missed out in this case, okay, because the third condition of stationarity I've really not stressed upon as of now. The third condition is okay the covariances between these different terms to the previous term. That is not able to be captured or corrected by this Z transformation itself. So that can still make your series non-stationary. Okay.
Got it.
So while you have put the mean, all of the mean same, and now that becomes 0. All of the variance same, that has made this one, but there's one more condition in defining a stationarity itself, and which is the relationship between the previous terms itself. Okay, so if the covariance must not be a function of the timestamp itself. It may depend upon a lag, but it must not be a function of a time lag. So if that's also coming into the play itself, so then your Z transformation is not really able to rectify that kind of a problem itself. Okay, so you really need to make transformations, to overcome that kind of a problem. Okay, yeah. Any other
Thank you,
question?
sir.
Sir, can you just see your chat box? I have some question, or I should speak.
Sorry, I didn't get your point. So there's something. Okay. And a stochastic variable mean is always constant. Okay, not necessarily. Stochastic variable can take any mean at all. Okay, so the example which I was just telling, that if it is a dice, rolling of a die, let's say rolling of a tossing of a coin followed by a rolling of a dice and 8 face tossers, dices, and a pack of card itself. Now in each of these cases, means are not the same. Okay, so if you define head or tail as 0 and 1, what is the mean value? 0 and 1, 0 plus 1 divided by 2, it's 0.5. Okay, in the case of a rolling of a dice, 1 to 6. Okay, 1 plus 2 plus 3 4 plus 4 plus 5 plus 6 divided by the 6 itself, 3.5. That's the mean. Okay, so mean of a coin tossing, dice, 8 face tosser, dices, and a pack of 52 cards. Their mean are not the same. But still, this is a stochastic process. Still, this is a time series data set itself. Okay, so stochastic variable can have have a very different mean values itself. Okay, the only thing is a stationary stochastic process should have a constant mean. Okay, but a non-stationary stochastic process can have a different mean itself. But these are still stochastic processes, and these are still part of the time series. Okay, so a series which is a non-stationary series doesn't mean that it is not a time series at all. Okay, that's just still a time series itself. Okay, so there are so many time series, and hence there are so many stochastic processes itself. But those stochastic process which exhibit stationarity, they should have a constant mean and a constant variance itself. Okay, so in stationary time series, mean is always changing. No, in a stationary time series, the mean is should be the same. Okay. Now, obviously, sampling sampling differences can arise. Okay, obviously, the mean of this value is somewhat sorry. So mean here, is here. But what you have observed is this one. The mean is actually the mean is here. What you have actually observed this one, but mean is here. Okay. So sampling differences can arise, but all of them are having the same mean. Okay. If it is a stationary process, then it must be having the same mean itself. Okay. So sample mean can differ, but at a population level, this must not be different. Okay. So only a stationary series should have had a same mean, a same variance, and the covariances or correlation should also be independent of the time point at which you are really been measuring itself. Okay? These are 3 typical conditions for stationarity, but at least first 2 I can still focus on, while drawing a conclusion regarding the basic nature of the time series data set. I hope I could answer most of the question. Still any question, any doubt to anyone?
So, sir, in stationary, you gave the example, and in that mean was increasing and continuously, like it is going upside. The line of mean is going upside, and variable are constant. All the variable were constant. So, is
variance,
it the condition?
Variance was constant. Okay.
Yeah, variance.
So to have a stationarity, the mean and the variance should be the same. Okay, that the example number one where the mean was the constant and the variance was also constant, that is a typically the feature of stationarity itself. Okay.
Okay.
So second and third
Okay.
example, that means including this one, these are typically the examples where the mean is not the constant and the variance are not constant, or both of them are not constant. Okay. So if
Okay.
mean as well as variance is also not constant, that again make your series non-stationary.
Okay. If they are not, then also it can be stationary.
Okay, so both of them has to be okay at least. Okay, these are basic condition plus one more condition that's on covariance itself. Okay, but at least be both these basic conditions, they must be fulfilled to say that series is stationary or not. Okay, however, there are statistical tests for checking for stationarity itself. But before we actually go for it, okay, you must understand that what is the basic nature, what we are really looking at. Okay, when we have been talking about stationarity itself. Okay, so if I'm saying it's a rolling of a dice and I have obtained certain number of observation, okay, now based on these numbers which you have obtained, okay, can you really able to comment upon that what is that random experiment out of which this number has been generated? Now I am telling you beforehand that it has been coming from a rolling of a dice. Okay, but if I don't tell you that this is coming from a rolling of a dice, and then you are supposed to make a comment that where from these numbers are really coming. Okay, now to able to answer this, okay, you will really be looking at, okay, these are all coming from, okay, the observation. Okay, if I just go back to the Excel itself. Okay, I just show you this. Okay, you see, okay, probably none of them are really crossing 6 is the max which you have been having. None of them are really going below 1 itself. Okay, and I don't tell you beforehand that is coming from rolling of a dice. So you will be making a conjecture that probably, okay, these observations which you have been getting, okay, and I can simply extend it to any levels itself. Okay, so probably I have obtained it. Okay, some okay, how many? There are 34 such observations which you have been having. Okay, or probably if I just drag it downward. Okay, so many observations. There are 548 observations which you have obtained. So this is a typical time series data set which you have been having, but none of them are really crossing, going below 1, and none of them are really going beyond 6 itself. Okay, so you can actually make out that, okay, it is lying between 1 and 6. Okay, so probably the typical nature of this kind of a time series that these numbers are actually coming from rolling of a dice itself. So you are better able to make a conjecture on. But suppose somewhere here, okay, you got a value which is 50. Okay, then you know that, okay, rest is perfectly fine, but there is 50 coming in between. That means this is not coming from a dice, because on dice, okay, you will never get 50. You will either be getting 1, 2, 3, 4, 5, and 6. You will never be obtaining 50. So probably this is something, okay, which I can't make really a conjecture that these numbers are actually being generated from rolling of a dice. It's coming from somewhere else. Okay, and if this has been happening, this is a typically non-stationary series. Okay, a non-stationary series, there is a sudden jump in the mean values as well. Okay, so you cannot really able to okay, comment on what is the underlying basic nature of the process itself. That's why you need the stationarity concept itself. Okay, but yes, there's a maths which goes to it. Okay, there is a walled equations which is going in between. There is, okay, ADF testing or KPSS testing which can also go, okay, but also understand. Okay, that's why I started my session with the quotation. If you are not able to understand, if you are not able to really explain it in a simple words, okay, that means, okay, you have not understood it well itself. Okay, so understand it, probably what I'm really doing. Okay, what is this basic, okay, nature of stationarity concept itself, why I need to be worrying about that. Okay, let's first be clear on that itself. Okay, and then you go for the okay, your data analysis. Okay, so you really need to check on these aspects. Okay, so stationarity helps you to really able to make a comment on the non-stationary sorry your stochastic process itself. So if you have a stationarity, you are better able to comment on the stochastic process, the nature of the random experiment, which is generating you the value. And if it is a non-stationary series, it's really, really difficult for you to make a comment on that. Okay, that's why you need the concept of stationarity. And that's why, okay, I said in the beginning itself, okay, if you have been working with the time series, okay, you will be encountering a problem with the stationarity itself. Okay, so what could be the consequences? Okay, that I will be, okay, coming next to it. Okay, but yes, okay, this is something which is quite fundamental. Okay, so I want each one of you to really, if you still have any question, any doubt, okay, because this is the premise on which I can work on any of the advanced concepts. Okay, so match to it, okay, the running of okay, but the test of it and making sense of those tests itself, okay, that's another aspect. Okay, but what you are really being concerned about, why you are really looking at, okay, these questions are, okay, something which you should be, okay, coming in your mind, okay, at the first place before you go for these kinds of testing itself. Okay, so still any question, any doubt to anyone, okay, please do let me know. Any other question, any other doubt to anyone?
Good evening, sir.
Good evening. Yeah, go
Yes.
ahead, please.
Am I audible, sir?
Yes, yes, you are audible.
Sir, can you please re-explain stationary and non-stationary with any practical example?
No, I'll come back to the stationary issue shortly as well. Okay, so I'll
Okay,
come
sir.
back to the issue of stationarity. Okay.
Because as far as we know something more about, I am confusing.
Well, I'll come back to stationarity, okay, one more time as well. I will show you, okay, with some glimpse of the data set as well. Okay, but
Okay,
before this, okay, before I move to that, okay, I really want, okay, you people to appreciate the fact that, okay, that you are able to understand it. What is a stochastic process? Okay, what is a
okay.
realization? And we are defining time series as a realization itself. Okay, and what
Realization,
could be those sorry?
realization mean outcome.
Yeah, so one typical outcome which you, one typical path which you have obtained, okay, as a output to a stochastic process is what is been referred as the realization. Okay, so
Okay,
just to
okay.
put, so here we said, okay, you have okay, a stochastic process where numbers are generated from a normal distribution which has okay, minus infinity to plus infinity range, and this is the data points which you have observed. Okay, and when you connect them, okay, that becomes your realization. Okay, so this realization is what is typically known as the time series. Okay, so here again you are having a realization. Okay, you connect them, this is also realization itself. Okay, again here this is your realization. Okay, and this realization is nothing what we are referring as a time series data set. Okay, so now let's move further itself. So we have talked about the time series. Okay, what exactly is the time series, and in the context of time series, what are the corresponding concepts of the population and the sample? Okay, so analogous concepts are, okay, the process and the realization, okay, rather than population and sample, and we worked on, we typically comment on that. Okay, still, okay, just for the sake of simplicity and connectivity, people do use the concept of population and sample, but okay, you don't have that kind of okay, connect there itself. Okay, so you should rather be, okay, using these words of process and the realizations only. Now, once you have a time series data set with you, okay, which is typically the realization of a stochastic process, how you try to analyze them. Okay? So generally, the time series data set is analyzed, okay, or really understood, or the behavior is generally been okay, assessed, okay, from at least three sets, okay, perspective. One is the time series plot, another is a parallelogram, the third one is the notion of stationarity. So that's why I was saying I'll come back to the notion of stationarity one more time. Okay, and we are having Okay, another there's called as the wavelet analysis as well. Okay, I'm not touching upon that itself. Okay, but there's also a wavelet okay, a way of really looking at the time series behavior as well. So at least these four are the one which is typically can be used to okay, assess the underlying nature of the time series data set itself. Now, so I'll touch upon okay some of them okay briefly today itself, and then I'll okay move to some more advanced concept at least for tomorrow itself. Okay, but the idea here is that probably you are able to connect the concept okay with your understanding that probably why what we are doing and probably why of what we are actually trying to do. Okay, that is something which you really need to be able to make a connect on. So you have a time series plot, okay? Not a big deal, okay? What is a time series plot? Okay, you simply plot the realization of a stochastic process on a line graph. That's all. Okay, so it's a time series plot. It's just a line graph of the time series. So you take the GDP of India, you plot it on timeline. Okay, that's a time series plot. Okay, no big deal. Okay? Not an issue at all. Okay. So this is okay some sort of okay realization of a value okay of a pure random okay variable which is simulated. This is also simulated. Okay, so it's not that okay they have been real data, but these are all simulated data where for each of these okay time point where you have been making an observation, it follows a normal distribution from minus infinity to plus infinity, and you have observed only one data point somewhere here. Okay, and same here for here. Okay, minus infinity to plus infinity, and you have observed somewhere here. Okay, and so on. So that's what is your stochastic process. Okay, data generation, and you are just plotting that itself. So this is your okay a simulated time series plot. Okay, but this is your artificial data. This is all cooked up data set itself. Okay, so this is not okay your real life data. But let's you can also have a look at some of the real life data set as well. Okay, now this is also okay a plot where there is some amount of drift has been there. Okay, so there's some amount of positive drift. It's going upward. The mean where observation is slightly going upward at each step, at each time point. Okay, the mean is shifting upward. Okay, with the shift in the mean, okay, you know that that makes your series non-stationary. Okay, so if a mean is shifting upward, if the mean is shifting downward, okay, so then that makes your series as non-stationary series itself, because this is also a non-stationary series. Okay, remember for stationarity, okay, there are three things which have been there. Okay, the mean must remain constant, variance must remain constant, and covariance okay should not be a function of okay time point. Okay, it may be a function of time lag, but at least not time points. That means if you are computing the covariance for 1997, okay, and you have been computing and the covariance for 1992, okay, so it must not be a function of a time point. Okay, it might be a function of a lag, that how much lag back okay you are computing the observation. That's a different thing. Okay, but that's also condition number 3. So I'm not too much focusing on the time the third condition. Okay, I'll come back to it okay slightly late, but at least and all the three need to be satisfied. So if this has been violated, so even if this is there, this one is also there, but the series has already been become non-stationary. So even in this case, if the mean is constantly being moving upward, this series is a non-stationary series, because at least the first condition has violated. Okay, all the three conditions need to be satisfied to say that the series is a stationary series. Okay, but okay, even a violation of any one of them can make your series as non-stationary. So this is also a non-stationary series. The last one was a stationary series, but this one is a non-stationary series. Okay, so this one was stationary series with no drift at all. They're all hovering around 0. Okay, and with their each of the observation following a normal distribution from minus infinity to plus infinity itself. But this is a cooked up series, this simulated series, okay, hypothetical data. This is a hypothetical data, but okay, a non-stationary series example because it has some upwardly drifting mean value as well. Okay. Now this is a series which is closing price of a stock itself. Okay, not a simulated one. Okay, it's a real life data set. You can plot a Sensex, you can plot Nifty, you can plot GDP, you can plot money supply, broad money M3 measure. You can plot the CPI index, consumer price index, or wholesale price index. Okay, for urban, for rural. Okay, you can put those indices. Okay, and plot it. These are typical series. Okay, the exchange rate, US dollar, and okay, USD, INR, and so on and so forth. Okay. Now, if you want to make a comment on the nature of the series, okay, so just okay, if you want to make a comment on whether this series is a stationary series or non-stationary series. Now, okay, as I said, okay, to have a stationary series, okay, three conditions must be fulfilled. Mean is constant, the variance is constant, and the covariance is not a function of time point. Okay, let's not too much focus on third. Okay, when I talk about the testing of a unit root, okay, I'll focus on third one as well. Okay, but let's focus on first and second itself. Now, do you think that this series is a stationary series? Okay, because if you compute a mean value at this range, okay, I'm only talking about mean. Okay, and you compute a mean value here in this range, you compute the mean value at this range. Okay, I'm calling it as M1 here, I'm calling them as M2 here, and I'm calling it as an M3. Do you think that three are the same? Okay. So there's a formal statistical way of checking for stationarity itself. But before you actually go for that formal test, okay, you can still make out by observing a data set itself. Okay? Do you think that three mean values will be the same? Okay, as opposed to if I go back here and what I do here, okay, I compute a mean observations. Okay, I take few of them here and compute a mean here. I take few of these observations here and I take few of these observations here. Okay, this is M1, this is M2, and this is M3. Okay, this is simulated, this is artificial, this is all cooked up data. So I know the mean value must be hovering around 0 only. Okay, so this typically should be moving around 0. This typically should also be moving around 0. This typically should also be moving around 0 itself. Okay, so M1, M2, and M3. Okay, I'm just taking it an artificial length itself, but they are typically going to be the same itself. Okay, here it's not so much prominent, but it is not the same, but at least this is quite prominent here. Do you think that the three mean values will be the same? Okay. Now, typically, this kind of a graph, okay, you can't really say that the three mean values will be the same, okay, and because the three mean values is not going to remain the same, this is a non-stationary data. Now, whether you go and make a statistical test, whether the series is stationary or not, okay, you can formally go for that itself, okay, you will come to the same conclusion because the condition number one is violated at the first place itself. Okay, so even if the second condition is there fulfilled or not, third condition is fulfilled or not, but the mere fact that the first condition is not fulfilled, this is a non-stationary data. Okay, so this series is a non-stationary series. Okay, now you can go ahead and make any formal test for that, but this is a non-stationary series itself. Okay, any question, any doubt on this? Why I'm saying that this is not a stationary series? Because here, when you have been observing, this is hovering around 275. Okay, so this is somewhere here, okay, which you have been computing an average here. The average here will be somewhere between 300 and 30 to 310, somewhere between that. So it will be hovering around 325. What will be the average here? Okay, that will be 410 to somewhere here 375, somewhat an average here. So mean here M3, the mean here which is M2, and the mean here which is M1. Okay, these are not the same number. Okay, they are not likely to be the same as well. Okay, given the graph itself. This is a non-stationary series. Okay, so it's not always that you go for some formal statistical test. Okay, and then say okay whether the series is a stationary or not. Okay, this is simply a non-stationary series. Okay? And this is typically the price data. And you can also see the same thing about the GDP. If you plot a GDP here, GDP will also be this ever increasing number. Okay, barring a few quarters, okay, due to pandemic or something else where you have a drop in GDP, but GDP per se, uh, expressed in terms of rupees, okay, lakh, crore, okay, that's a denomination in which, okay, 16 lakh crore GDP amount. Okay, so if you state it in terms of the level, not growth rate, but in terms of level, okay, this will be an ever increasing function. You take a money supply, okay, broad measure of money supply, that will again be, okay, typically okay, not just broad or narrow measure M1 as well. Okay, this will typically an increasing function. That's also a non-stationary series. You take the consumer price index, okay, you plot them, that will typically again be a non-stationary series. Okay, and the reason lies the same thing. You take a, okay, section of the data set, compute its mean. If it is a stationary series, the mean would have been the same, but it is not. Okay, this is not a stationary series at all. Even a one single jump can make your series non-stationary itself. Okay, let's take the next example. To take this one, okay. Any comment, okay, whether this series is a stationary series or non-stationary series?
It is non-stationary series.
So if I okay, or let me put it in this question in two parts. Okay, if I simply take, okay, a time range which is somewhere here onwards.
It has structural break.
So if you take
It's
the
stationary.
series which is, okay, if you take a series which is beyond this time point, more
Then
or
it is
less same.
stationary, sir.
Okay, more or less same itself. So this is stationary. If I take it somewhere before this, okay, that is still a stationary. Okay, somewhere
It has
here.
just one
But
extreme
the
value.
moment you have this kind of a shock, okay,
Then
so what has
difficult to
happened
say.
here? Okay, so when you have this jump, okay, obviously the mean, if I now draw a distribution here, okay, and if I now draw a distribution here, are the nature of the features of both the distributions same?
No, sir.
Okay, no. So that makes my series as non-stationary series. Okay. So what makes my series? Okay. What makes my series as non-stationary? One of the reasons for this kind of a non-stationarity is these kinds of a shocks itself. So shocks also make my series non-stationary. Okay. Shocks also makes my series non-stationary, and so typically, okay, making my shocks, okay, is also one such reasons which is non-stationary. Another okay reason for okay the series is becoming non-stationary is the drift. Okay, somebody asked, okay, probably what is the drift? Okay, so let me just. Drift is a trend itself. So here what I meant was, okay, that it has a drift. Okay, what actually I meant by drift is that, okay, every time point, okay, your values is okay slightly higher itself. Okay? So that means if you have a trend, so mean is a function of a time. Okay? That's what I meant by, okay, having a trend in the series, and that's what I meant by having a drift. Okay? So drift means that your obviously here the mean is constantly, okay, as you move across the time, the mean is constantly shifting upward itself. Okay? So it's been drifting upward. Okay, that's what I meant. Okay, so this is also a non-stationary series. Okay, so the trend, the presence of a trend in the series can make my series as non-stationary. Okay, the presence of a shock can also make my series non-stationary as well. Okay, so the series can become, okay, non-stationary due to, okay, multiple, okay, such reasons, individually or combined as well. So if it is, okay, you are also having a drift and as else also, okay, shocks in between, that can also make my series as non-stationary as well. Okay, so at least two reasons you have already figured out, okay, for the holding the non-stationarity itself. Okay, and that you can make out from, okay, from by looking at a graph itself. Okay, so you want to go for formal testing as well. Okay, yes, go ahead. Okay, if you write it in your research paper on in your thesis, okay, by looking at a graph, I guess, okay, the series happens to be exhibiting a behavior of non-stationarity, okay, people will not accept it. Okay, so probably you need to give them some statistics, okay, that tells you, okay, that series is non-stationary. Okay, but it's not always that the, okay, the required itself. Okay, if you show them that this is a series, this is a non-stationary series. Okay, so whether you give a statistics, okay, that confirms what you will be saying. Okay, but okay, there is no need for really, okay, looking at a statistics and saying the series is non-stationary. This is a non-stationary, I know. Okay, because the mean is constantly shifting upward itself. Okay, so there's some sort of a trend which has been there. If you have something like this one, okay, this is also non-stationary series, I can make out, because here, okay, my mean, what is the mean here, what is the mean here, what is the mean here, what is the mean here. Okay, these are not the same, they are, okay, they are different from each other. That makes my series as non-stationary itself. Okay, but okay, but to really look at, okay, this kind of a non-stationarity itself, okay, another way, okay, probably you will really be supporting it with your, okay, formal statistical test, ADF, KPS is another itself, but the series is a non-stationary series. Okay. What is the difference between this kind of a series and the white one, the original, this series in the presentation itself? Okay, this has a trend and this also has a trend. Both of them are called as a trend. Okay, while the trend here is referred as deterministic trend. Okay, because, okay, it's a constantly upward secular, okay, exponentially moving upward trend. Okay, so that kind of a trend is called, referred as deterministic trend. This kind of a trend, okay, because there is no trend, okay, secular trend, okay, constantly going down or constantly going upward, this kind of a trend is called as a stochastic trend. Okay, but there is a presence of trend. Okay, so mean are not the same in this my hypothesized red line and this white line. Okay, so there is a presence of trend in both these cases, but due to that, okay, both the series happens to be the non-stationary itself. Okay, so typically what you can observe is that, okay, three things can make your series non-stationary. Okay, presence of a trend, okay, which could be deterministic, which could be stochastic, but that can make your series non-stationary, and the presence of shocks that can also make your series non-stationary. And okay, that's also, this information is also useful for your, okay, After Effects itself. Okay, how can you make a series stationary itself? If it is affected by trend, okay, you detrend them. Okay, Detrending and deterministic is okay. You detrend by virtue of okay your detrending okay is something which you study in your okay, undergrad itself. Okay, that you will decompose your time series from your trend component. Okay, so from the y you deduct y cap, where y cap is arrived at from alpha plus beta t. Okay, so you detrend them. Okay, that's the one way. Stochastic trend. Okay, you can handle it by differencing. While how you handle shocks, you put a dummy variable, okay, that can also handle for shocks and that can make your series as stationary itself. So what is the cause of the non-stationarity? Okay, can be used for your rectification, okay, of the non-stationarity of the data set. So you can use that. Let's take this one. Okay, this is also a shock. This is also a shock. What is the difference between these two series? Okay, if it is a shock, definitely this is non-stationary. Here again there is a shock. Again, this is also non-stationary. Both the series are non-stationary. But what is the difference between this first series and the second series? What is the difference between
So
these two
here
series?
it is a drift rather than shocks, I think.
The shock is there in both the cases because this is a shock. Okay, some demonetization has happened. So as a result of which, okay, you were having some UPI applications. Okay, but demonetization has really increased it. Okay, so these kinds of shocks has been there. Probably an apt example is this something like this one. Okay, so digital payments you have been doing it, and then there's a demonetization. So digital payment has increased, and but from there onward, okay, the digital payment has really not come down. Okay, it has still been increasing itself. So their shock has been there in both the series itself, this one and this one. But here this kind of a shock is referred as, okay, or rather this kind of a series is referred as mean reverting series. You had a shock, the effect dies out, and then you are okay, continue with your original path which was before the shock itself. Okay, while here what has happened, okay, you are following some path, then there is a shock. Okay, after the shock it does not come down and then follow the original path. Okay, after the shock it takes on the new path itself. This is mean fleeing time series. Okay, so you have a mean reverting time series where after a shock you come back to your previous level, the original levels, and okay, this kind of a series where there is a shock and then you take a different trajectory altogether. You take a different path altogether itself. Okay, analyzing a mean fleeing is also okay a difficult aspect itself. Okay, so for when we talk about some sort of a Garch models, which is again part of the time series model. So if your alpha plus beta values are greater than 1, you are having a mean fleeing time series. Again, very difficult to make a forecast itself. Okay, so but you do have these kinds of time series itself. Okay, so these are still time series. Okay, non-stationary time series are also time series. Stationary time series is also time series. Okay, but stationary time series are forecastable. Okay, testable. Okay, interpretable. Okay, make an estimate. Okay, point estimate, make a okay interval estimate. Okay, that can be easily done. But non-stationary series are not okay really used for okay testing for hypothesis and construction of a confidence interval because they lack the basic attributes itself. Okay, so this is also one such time series. Okay, okay. So yes, that's also an important question. So probably why the fuss all around, why I should be really worrying about times, the stationarity in the time series itself. Okay, okay, so
Sir, can you please repeat to make it stationary in case of shocks? We need to do what?
you include the for that particular shock, you include the dummy variables for that.
Okay.
You include the adjust for the shocks itself. Okay. Now I have one more example before I actually comment on okay a question. It is a very important question okay, as to why this fuss all around? Why I'm so much focusing on the stationarity? Okay, what the hell? Okay, will fall upon your head. Okay, if you do not have a stationarity. Okay, so a little bit before I answer that question, okay, let me continue with some of these. Okay, so this is an example of a mean reverting time series. It has a shock, and if you can adjust for the shock itself, okay, the series will otherwise become stationary itself. Okay, otherwise, given the shock, the series is a non-stationary. Okay, so if you have shocks in your data, you need to account for those kinds of shocks itself. Okay, so this is a mean reverting, this is a mean fleeing. Okay, now you also have a look at this kind of a time series itself. Okay, so these are, sorry, these are two time series. Probably one you can take it as Sensex, another you can take it as Nifty. Okay, you can take, okay, any other one. You can take it as WPI, another you can take as CPI. Okay, consumer price index and wholesale price index. Okay, so you can take some of these pairs itself. Okay, so you do have. Okay, so if you now look at individually, the blue line at a time or a red line at a time. Okay, do you think the series is stationary? Is the red series stationary?
No.
Stationary.
So somewhere here, average here, some average here. Okay, some average here. Okay, these means are not the same. Okay, so the red line is non-stationary. Okay, is the blue line stationary?
No.
Okay, that's also not stationary. Okay, again the mean values are differing. At least mean values are different. Probably this is the way I should quote. Okay, variance could also be different. Okay, which I'm not really able to observe. Okay, so, okay, clearly by looking at a graph. Okay, but at least I can make some sense about the mean itself. The mean values are not the same, so the series is not stationary. Okay, so individually the red series is non-stationary, individually the blue series is not stationary itself. Okay, but if I ask you, if I take a vertical distance between red and blue, okay, so red minus blue, whatever you call it, whether red is Nifty, sorry, Sensex, and blue is Nifty, or red is consumer price index and blue is, okay, the wholesale price index. Okay, whether you take some of these pairs itself, but I'm taking a vertical distance. Okay, do you think that's stationary?
Yes, sir, because difference seems to be same everywhere at every
Now,
point.
so differences, so if you take a difference and you try to plot them, probably the difference is, okay, hovering in a range. Okay, it's not coming up, okay, very high or very low, but that seems to be, okay, hovering at within the range itself. Okay, so when you have something like this, okay, where you have a non-stationary series, another series which is also non-stationary, you can have not just two, you can have three more. Okay, five, six. Okay, and so many more itself. Okay, but when you have series which are individually non-stationary, but, okay, with some combination, and taking a difference is also a combination. Okay, which is stationary. Okay, so the difference is the stationary, but, okay, when you take them, okay, individually they are non-stationary, then that series is referred, that set of series is not a single series, that set of series, that means red plus blue, okay, is referred as co-integrated series. Okay, so you also have, okay, one more topic in time series which is referred as co-integration. Johansson's co-integration. You also have Engelgrenzer co-integration. Okay, but what is an idea of co-integration? The idea of a co-integration is, okay, here that a combination of the two series exhibit stationarity. Individually, they are non-stationary, but a combination of them is really exhibiting sort of a stationarity. So this is also, okay, your this kind of a series is referred as co-integrated series itself. Okay, clear? Any question, any doubt to anyone here? Okay, so there could be series which are non-stationary series individually. If you observe them individually, like in this case, red and blue series, if you take them one at a time, red once and one more time blue only, if you observe them, okay, they happens to be non-stationary series. But if you take a combination of them, okay, taking a difference is taking one, is one such combination. When if you're taking a difference here, that seems to be exhibiting, okay, sort of a stationary behavior. Okay, so if the difference of these two series is showing you some sort of a, okay, stationary behavior itself, okay, then these series are referred as co-integrated series. Okay, still any question, any doubt here to anyone?
Sir, I have
Okay.
a question.
These are still building blocks. Okay. Oh, yeah. Yes, go on.
Sir, I wanted to know this time series. This is a technique of data presentation, or we can use it as for hypothesis testing also.
No, so if you have a data which you use it for at least three purposes, you generally use your data for. Firstly, okay, is for your hypothesis testing and making a forecast. Okay, establishing a relationship between them. Okay, making a forecast. Okay, having a hypothesis testing, and okay, construction of a confidence interval. Okay, around that. Okay, so you generally use a data set for these purposes. These are typical purposes for why you meddle with okay, get your hands dirty with the data itself for these typical purposes. So if you want to go into that itself, okay. So time series, okay, data set is no different from any other data set. You can go ahead with that itself. But with time series, okay, there are few things which you really need to be, okay, careful of. Okay, and the aspects, okay, that's what I've been trying to highlight in this particular, okay, session itself. Okay, so
Yes,
seasonality is one aspect. Okay, the okay, but the concept of population versus, okay, sample is another aspect, and typical violation of this kind of a regression relationship is the presence of serial correlation, which is also the case, which is there with the time series. So you need to handle them, okay, with care itself. Okay, any other question, any other query to anyone? Okay, so now let me move to this very vital question. Okay, why we check for the stationarity? Whoa, okay, what the hell on earth will fall upon your head? Okay, if you ignore the stationarity itself. Okay, so why should be worrying about the stationarity itself? Okay. Okay, so you have run a regression. You have tried to relate the variables of your interest, and okay, which are non-stationary. You have run a regression, you have interpreted them, okay, and how does, okay, that really be okay, affecting your results? Okay, so I'm just giving you an example, okay, from a published research, obviously. Just move forward a bit, fast forward somewhere. Yes, here. So, okay, so I'm giving you an example here. Okay, these are the examples, and these are all examples of non-stationary series. Let me tell you beforehand itself. Okay, what are typically the way in which you can judge whether you have, okay, run a regression which is a good regression result? Okay, typically you go for R square. Your R, if your R square is very high, that means, and what does the R square tells you? It tells you what is the percentage of explanation. Okay, explanation of what? Explanation of the dependent variable provided by the independent variable. So how much of the independent variable explain the dependent variable? That number, that magical number, is given by the R square. Okay, so which tells you about the model fitness as well, that how good your model is. Okay, so I'm giving you an examples, okay, of okay, typical non-stationary series. They have run a regression, and then, okay, the result output, okay, the output is actually been presented on the slide itself. Okay, so let's take first one. Egyptian infant mortality rate. Okay, so infant mortality rate of a country which is Egypt. Okay, that's your dependent variable. And what are your independent variable? American farmers gross income, income of American farmers. Remember Egypt, okay, country's infant mortality rate, American farmers, okay, income, and money supply of Honduras. Okay, probably some of you may not even heard of this country. There is a country called Honduras. Okay, so there's a Honduran money supply. Okay, so probably you can have a Google search. Okay, what is the name and placement of, okay, geographical placement of for this country Honduras? Okay, but that's also one more variable. So Egyptian infant mortality rate is explained by the American farmers income and Honduras country's money supply. Look at the R square, 0.918. That means 91.8% explanation of the infant mortality rate in Egypt is explained by the American farmers and Honduras money supply. So America and Honduras, okay, economic or non-economic activity, okay, especially these are financial activity, economic and financial activity affects the infant mortality rate of Egypt. And the explanation is almost 92%. So 92% of the infant mortality rate is, in a way, if you try to conclude it that way, is caused by American farmers and Honduras money supply. Okay. Now, these are the typical example which has been taken for an unrelated data. Okay. Here you can, if even if, okay, I give you this kind of statistics, okay, and, or I don't give you this kind of statistic, I simply ask you, okay, verbally, okay, do you really think that the Egypt's money, the infant mortality rate is, okay, can be related somehow, okay, by the American farmers income and that of the Honduras money supply? At least the Honduras money supply, can that affect the infant mortality rate in Egypt? Okay, your answer should have been, okay, I hopefully, okay, that no, okay, that should not be affecting. Okay, I don't have any theory, I don't have any plausible explanation for this kind of a reasoning itself. Okay, so these are all examples, these 5 examples which have been presented on the screen. These are examples of a variable which is totally unrelated at all. Okay, you don't have any relationship, no theoretical relationship between these variables itself, and they have been chosen for that same purposes. Okay, the problem lies that probably if you take something which is of related, okay, so you take the Egyptian money supply and Egyptian infant mortality rate, okay, then it will start ringing a bell, but you will still be having such a high correlations too. Okay, so these are a typical example of uncorrelated, okay, unexplainable, theoretically unexplainable data set. But if you go by the numbers, okay, it's a very high correlation. Okay, lot of explanation which has been provided. Okay, so it has been affecting that. Okay, and typically the nature of this is that infant mortality rate and the aggregate income of American money supply, sorry, farmers, money supply, these are all non-stationary data. But when you put them together, you try to run a regression, you get a very good model fitness. Okay, and these are all being affected by, not because of the fact that they can really explain the dependent variable, but all because these are non-stationary. They are being affected by either shocks or trend, and because they are being affected by simultaneous shocks or trend or both, okay, they give you these kinds of high explanation, but there is theoretically no explanation for these variables itself. Okay, so if you try to run a regression on non-stationary data set, you will, okay, fall into this kind of, okay, result, which is what we generally refer it as the spurious regression results. Okay, so if you have run a regression which is on non-stationary series, the chances are that you will run into, okay, a trap called spurious regression. Okay, and these are all real life data, these are not cooked up data, these are all real life data. It's a real Egyptian infant mortality rate taken for this time period in an annual data set, exactly the real data set with which these regressions are being run. Take another one, US
Sir,
export.
I have a question. Sir, I have a
Yes.
question. Shall
Yeah.
I? Sir, in first example, you explained that infant mortality rate is one variable, and some money supply of some country you are saying is another variable. These are two unrelated variables. So we cannot take them under regression. But then how unrelated variables? I mean, like I'm confused with that unrelated variables and non-stationary. Is it same?
No. Okay.
Non-stationary characteristics of
If
data,
if
is it
call
same
out.
as having
Okay.
a relationship between checking a relationship
Problem with
between two unrelated variables?
the point which I'm just bringing it forward is itself. Okay. If you have non-stationary time, okay, obviously you've been working on time series. All these are time series data. Okay, 97 to 99. Okay, 60 to 90. Okay, these are all time series data. If you have a time series data, and the time series data with which you are working happens to be non-stationary, okay, then the chances are that you might get a high R square, and you fall into a trap and you'll say, okay, I have a very good model fit and I have a perfect explanation. Okay, though theoretically there is no explanation which has been there, which has been evident by relating unrelated variable, unexplainable variable itself. Okay, problem is accentuated when you have a time series data, when you which are non-stationary series, okay, and which are related, somehow related. So okay, so you take money supply and you take GDP, you take both India's money supply and India's GDP itself. You run a regression on that. Can you run a regression? Okay, yes, there is a monetarist
Yes,
perspective.
sir.
Okay,
Yes.
so you can run a regression. Okay, you try to explain, but this explanation which you have been trying to do will fall into the same trap itself, that you will get a very good R square irrespective. Okay, but I've not even looked at the data. Okay, I've not taken the M3 data, I'm not looked at the GDP data, but I can foretell you rather, okay, before you actually do it and see it yourself with your own eyes. Okay, you take both these data and you run a regression. A typical R square which you will be getting is above 80%. I'm telling you beforehand. Okay, so you might try to conclude that the monetarist approach works. Okay, but that's not a correct explanation. It doesn't work. Okay, because both these series are not really affecting each other. Just because this happens to be trending upward, which is your deterministic trend, which makes your series non-stationary. This is also typically deterministically upward trending series, because both these series are okay, deterministically upward moving, which is manifested by their basic nature, that this is also non-stationary, this is also non-stationary. I've already talked about the presence of a trend makes your series non-stationary. So both these are non-stationary. Just because both these series are non-stationary, at the back of it, because there happens to be co-trending with each other, okay, you might try to conclude that money supply is affecting GDP, but that's not a correct explanation, because just because the two series are moving upward with no relationship at all between them, okay, is not really the explanation which you can really have it. Okay, or so something like that. Suppose that there's a money supply shock here, okay, and there is GDP supply shock there as well. Okay, so in both these cases, because there's a shock there, okay, which again makes your series non-stationary, and you try to explain, okay, the two variables are perfectly explaining each other, or closely explaining each other, 80% explanation, which is very good explanation itself. Okay, that's where the problem lies. Theoretically there is no connect. Okay, the statistical evidences are absent, but just because of the presence of trend, stochastic or deterministic, or the presence of shock, all of which is getting manifested in terms of non-stationary series, you might try to conclude that there is a heavy explanation of one variable over the other. However, the explanation is perfectly spurious. There is no correlation at all. Okay, there's no explanation. There are no statistical evidences of supporting this kind of a explanation itself. So you might run into that kind of a trap. Okay, that's what has been explained by this kind of example. By taking okay, definitely those series where the explanation is certainly not there, because there is certainly no explanation for Egypt America, and Honduras. Okay. So that tells you the same thing. Okay. That this is non-stationary series. This is non-stationary series. Okay. American life expectancy, non-stationary. Export, US export, non-stationary. US defense expenditure, non-stationary. Population of South Africa, non-stationary. Total crime rate, United States. Okay. These are non-stationary variable. When you try to relate non-stationary variable with another non-stationary variable, okay, you might get pretty good R square, 91.8, 91.6, 94%, 81.1%, 97.4, or best of it. Population of South Africa explained by R&D expenditure done in United States. So R&D, you do R&D in United States, and the population of South Africa is increasing. Okay, with any theoretical logic, you will not be able to explain, but probably okay if you okay, but you do get okay pretty high R square just because of okay the presence of non-stationarity itself. But the situation becomes more problematic when there is a population of America and the R&D of America itself. Okay, then you start okay your heart starts to support the hypothesis that there is a connect, but there is no connect. Okay, why the two are really showing you a very high R square is because okay, either they have been having some sort of a presence of deterministic or stochastic trend between the two variables, or shocks, okay, or all of them together, making the two series non-stationary. When you try to relate a non-stationary series, you might come up with this kind of a okay this kind of okay, a trap regarding the okay high explanation of the variable. The
So my
point which I'm
question.
just trying to make, just let me conclude with the
Yes,
statement
sir.
itself.
Yes, sir.
Okay. So the point which I'm just trying to conclude is that if you are working with a time series data set and you happens to have a non-stationary series, okay, don't run regression. Okay, so you must not. Okay, so what is the rule? Okay, the cardinal rule is do not run regression with non-stationary series. That's a rule. Okay, so never ever run a regression on non-stationary. Never relate the stock price with the market index. Never run a GDP with that of a money supply. Never run with with the inflation index with that of okay the unemployment data. Okay, never ever run this kind of a regression results. Okay, they will most likely be, because all these series happens to be non-stationary, you will be getting a result which is a spurious result, which do not have any economic explanation, just because of a trend, stochastic or deterministic, or for that matter the shocks itself are making you look that the data is really okay falling in line, and you have a okay explanation to a theoretical okay concept itself. Okay, so this is the rule which has been there, with only one exception. There is a one exception, okay, to this kind of a rule, which is the Nobel Prize winning work. People have earned a Nobel Prize for that exception itself. Okay, but the rule is still there. So you must not run a regression on non-stationary series. Okay, so in an effort to trying to explain, okay, answer that question, what the hell on earth, okay, why we should be worrying about stationary. If you do not worry about stationary and you are still working on time series data set, you might run into a problem of spurious regression. Okay, yeah, any questions?
So how can we find out statistically whether whether a series is stationary or not? Is there any
Yes, there are ways.
provision in SPSS software?
SPSS, I'm not sure, but yes, there are many such free softwares where you can look for. Okay, so these are the typical tests which you have. Dickey Fuller test, augmented Dickey Fuller, okay, GLS, ERS test, Philip Perron, KPSS test. These are the typical tests, okay, by which you can check whether your series is a stationary series or a non-stationary series. Okay, and these are available in almost many software, okay, which are focusing on time series. Okay. Generally, SPSS is not too much focused on time series. Okay, but yes, okay, any including okay, you have eviews, stata, okay, R, Python, Gradle. Okay, so you have so many options. Okay, R, Python, Gradle, they are all free, open source. You can download it and use it. Yes, Stata, eViews, okay, these are typically the proprietary software, okay, paid software, okay, but you'll find, okay, but testing for these kinds of attributes statistically as well. So they are formal statistical tests for stationarity itself. So there's a stationarity, okay, test for, okay, good determining whether your okay series is stationary or not, okay, and it works on all the three conditions. Mean, they check for whether the mean is constant, okay, variance is constant, and covariance is a function of time point or not, okay. So they check for that, okay, and formally present you whether the series is stationary or not, okay. But my point here was, okay, before you actually go for that kind of formal testing, by looking at the graph, you can also make out, okay, whether your series is a stationary or not. Okay, so this is stationarity is really not so much of, okay, of mathematical and the abstract concept, okay, that you need to follow it so such a religiously itself. Okay, the idea there was that, okay, you understand that what do I mean by that stationarity, and why do at the first place I need stationarity itself. Okay, so yes, there are, okay, softwares for supporting that as well. Okay, so I was just naming the eViews. Okay, we're having Stata. These are paid. Okay, then you have R, you have Python, you have Gradle, and many more. There are soft, okay, open source as well. There are so many which are big there. Okay, so probably SPSS is not too much on time series. Okay, it doesn't, okay, give you so much on the time series itself, okay, but cross sectional wise it gives you much more than the other itself, okay. So typically these softwares, okay, they are not offering that much what the SPSS has been offering for a cross sectional data set, but for time series, okay, EVU's data have been offering more than what the SPSS have been offering that itself. But yes, there are free, some of these free versions as well, which you can use it for this kind of a checking itself. Okay. Yeah. Any other question? Any other doubt to anyone? So be aware of the fact that whenever you are, okay, running a regression, or, okay, putting the two variables together, and that happens to be non-stationary individually, okay, then you must not run a regression on. Okay, so this is a cardinal rule which you must be following always. Okay, whenever you are working with non-stationary series, is never ever run a regression. Non-stationary regressions are likely to result into a spurious regression itself. Okay, so these are fake results which you will be obtaining. Okay, the problem is probably if you rely on that, okay, then probably, okay, you have some absurd results to be really, okay, supported by, okay, some chance itself. Okay, so you
Sir,
should not be making
so can
yes.
sir, only regression or any kind of hypothesis testing, for example, t-test and other? Can't we
No,
run any of them? Or
you can run, okay, a regression, okay, sorry, should not be, okay, okay, running a regression. That's the first place. Okay, regarding the okay, individual univariate analysis, okay, because your regression is a bivariate, okay, or multivariate analysis itself, okay, with the kind of regressions, model which you have been running. So regarding a simple t-test, mean checking another, okay, again, remember, if you go for a t-test, what are the typical, okay, assumptions which are involved in a t-test? Okay, t-test assumes that sample is drawn randomly, okay, which is perfectly fine. Okay, you are making an assumption that it's a stochastic process. Okay, it's been perfectly fine, it's been following. Okay, but then you also make an assumption while going for a t-test. Okay, sample is drawn from the same population. Okay, that's also one more assumption at the back of it, if you could recall. Okay, when you studied a t-test, okay, of a mean, whether your mu is equal to 30 or not, if you want to check. Okay, That's a test you want to conduct, and you are having a time series data. Okay. Now, for conducting this t-test, you made an assumption that the sample is drawn from the same population. Okay. If you are having a non-stationary, and I gave an example of non-stationary, something like that, that you are rolling of a dice, which you are doing it once, two, three, four, and then after a while, if it is okay, a pack of 52 cards, okay, obviously this series is a non-stationary series, okay, then you made an assumption that sample is drawn from the same population. Is it the same population? Dice and pack of card, is it the same population? The answer is no. Okay, the observation which you are getting from the rolling of a dice and the observation you are getting it from a pack of 52 cards, okay, so they are not the same. Okay, the mean has been shifting upward, the variance has also been higher. Okay, that makes your series non-stationary. But that typical thing, okay, is also been okay, in a different format. It's still been coming into the play, that when you go for t-test, you make an assumption that sample is drawn from the same population, which is not validated. Okay, so that feature of non-stationarity somehow also plays, okay, these differently in your univariate versions as well. But if it is fine, okay, probably you can ignore the times
But
the
sir,
stationarity.
for example, I have a change in debt and change in equity. Every year, what change has been occurred in debt and equity of a single company or multiple companies? In that case, can we compare the change in rate of change in debt and rate of change in equity with t-test for a single company or ANOVA for multiple companies? Is it possible? Because that is time series data, but you said that if we make it a rate of change, then it will become stationary. So is it possible to apply t-test or ANOVA on this kind of data?
Once it is stationary, then there is no worry. Okay, so once the series is stationary, you can run a regression. Once the series is
Okay.
stationary, probably this assumption is also been upheld, that you are drawing it
Hmm.
from the same population, because that's the
Hmm.
whole idea of saying the stationarity, that it's the same random experiment, okay, which has been observed over time, that has resulted into your okay, the observation itself, which is your stationary data set itself. Okay, so that if it is already a stationary, then you don't have any problem. Okay.
But
But
still, if it is not stationary,
if you take
huh.
only debt levels, not
Hmm.
change in the debt equity, but you take a debt levels. Debt levels typically will be a non-stationary data. Change in debt equity, I'm just making a conjecture that probably this will be a stationary. Okay, I'm not sure, okay, because I really need to see more attribute. But typically, the debt levels will be a non-stationary data. If you try to put a t-test on this data, okay, then this assumption of same population, okay, might not hold true. For example, okay, somewhere down the line, the company has merged, and as a result of which the debt level has risen. So the debt levels was almost the same, but there's a merger happening, and okay, from a dice you have shifted to a pack of 52 cards. Okay, so there's altogether a new mean and variance which has been okay come into the play. So this assumption is not been valid. Okay, and hence your t-test results will also be invalid as well. So you can't check for the average debt levels. Okay, but yes, change in the debt equity levels. Okay, if it is supposed to be stationary, okay, you can go ahead and go for the formal t-test itself, univariate analysis, no regression done.
Okay, thank you so much, sir.
Sir, will you be covering structural break?
Structural breaks, okay, not in a formal way. Okay, probably I've only talked about that there is, okay, you include dummies, okay, to include for the okay breaks in between. So if you have something which is like here,
Just one query, whether we can run that with non-stationary time series data, or compulsorily we have to use stationary data?
you should, okay, but only one exception I said, okay, you need to run that. Okay, so I think I had this, yeah, okay. So you do have a structural break here, okay, but here the structural break is what, okay, So the nature, the structure of the data set has actually changed. Okay, so there's a slope change here. Okay, so how you incorporate change in the slope using a dummy variable, that's a different way. Okay, and that typical example which I had, okay, I think this one. This one. Okay, that's not slope change. Okay, this is one such, okay, change itself. Okay, so there are different way of in which you can incorporate, okay, the structural breaks in your data set. So this is one way, okay, by simply having, okay, yt is some alpha plus beta plus, okay, so on, so on, some beta 3 into dummy variable, which is for this particular time span. Okay, so that's typical the way when you can handle a structural break, okay, in your data set itself, and then the series will come up as a stationary itself. But for the another example where the slope change was been happening, okay, from somewhat like this, okay, and was happening, okay, so you need to include, okay, dummy variable, okay, slightly differently itself. So beta 3 into xt into dt itself. Okay, so that is another, okay, way in which you can incorporate structural breaks in your data.
And for locating a structural break, we have to use a stationary or non-stationary will do.
Okay, yes, okay, for location as well, okay, graph can tell you, okay, probably where the break lies, okay, and then there are also tests for that. There are chow test for a known, okay, break date, okay, then there are, okay, multiple break as well, okay, I think by Perron test, okay, so if test is also been there, which can tell you that there could be multiple such structural breaks in the data set. So by in the case of chow test, you know what is the break date, okay, something like demonetization. Okay, so you know the date exactly where the break in the structure really happened. Okay, and you can go for it, whether it was significant enough to be incorporated in your analysis, or you can let the data tell you that how many structural breaks have been there, and then you relate it, okay, what actually has happened on this particular day when the prices were so much high itself. Okay, so you see for some of those, okay, breaks in your data set, and you incorporate in your analysis.
Okay, so for that I need to see the change or the absolute value will do.
The absolute value adjusted for the break, okay, should make your series stationary on example something like this one. So here you observe that probably, okay, the range in which this has been incorporating, okay, sorry, okay, this values are been actually been hovering, okay, they are almost, okay, mean wise they are common, they're same, okay, for different levels, but only for this, barring this one, okay, everything else is the same. Okay, so probably here you can have yt, okay, with 12 some alpha plus, okay, your any dependent variable, sorry, independent variable you might have included, you would have include one more dummy. Okay, so some beta 2 into d, okay, which takes the value equal to 1 when the time is, let's say, okay, 3, otherwise it's a 0. Okay, so it incorporates that. Okay, so then that makes, because if you take it on the other side, that will be yt minus beta 2 into dt, okay, plus alpha plus beta xt itself. Okay, so now this is, okay, break adjusted yt series. Okay, and that is already, okay, so stationary, so that will make your series stationary altogether, but you need to include your break in your model itself. So you need not take a difference of this kind of a series. By making adjustment for the dummy, accounting for the structural break, that makes your series, okay, stationary, but not this one. Okay, so even if you include the dummy, okay, for the break in your analysis, okay, that will still not make your series, okay, stationary. So this will something, this range will be shifted upward. So this will be something like, okay, this itself. Okay, now this is still, the series is still non-stationary itself. So even if you include your dummy, okay, that doesn't make your series to be stationary. So here you need to account for both. Okay, include the dummy as well as go for, okay, the differencing, okay, if that helps, or detrending. if that helps.
So for locating the structural change, I can use this data. But for regression, I have to make it stationary. Am I correct, sir?
No, okay, but you need to only run regression on stationary data.
Stationary, yeah.
Okay, so convert your series into from non-stationary to stationary.
Yeah,
Okay.
that is what exactly I want to check, sir.
So you detrend it, you difference it, and you account for a structural breaks. 3 options to be taken individually, one by one, or in a group. Okay, but that must be done to make a non-stationary series as stationary. And once you have a series stationary, you run a regression on that.
Okay. Thanks.
Yeah. Any other question? Yeah. Okay. That exception as well. Okay. The Nobel Prize winning work of okay. What is the exception to that rule? Okay. So exception to that rule is that okay, do not run regression on non-stationary series. Okay, that's a rule. Okay, so never ever run a regression on non-stationary series. Okay, otherwise you will run into a problem of spurious regression results. Then then what is an exception? I said there is an exception to this rule. Okay, the exception to this rule is coming from here. Remember I talked about co-integration. Okay, if you are having series which are co-integrated series, okay, so if you have series which are co-integrated, and I have already talked about the co-integrated series, that okay, individually these series are non-stationary, but when you take them in a combination, differencing the two series is also a combination. Okay, so suppose the red series is R, the blue series is B. So if I take it 3R plus 4B, that's also a combination of R and B. If I take 1R plus 4B, that's also a combination. If I take it 1R and minus 1B, okay, that's also another series which literally means R minus B only. That's mean taking a vertical distance between the two. Okay, that's also combination. So when there are two series or two or more series individually which are non-stationary, but when you take them in a combination, any linear combination, okay, and which makes them look stationary, which you are able to observe it here, that probably their vertical distance is is a stationary series, then those series are referred as co-integrated series. Okay, so when your series are co-integrated, then you can run a regression with non-stationary series. Okay, so I again repeat the rule as well as the exception. The rule is, okay, do not run a regression on non-stationary series, and the exception is if the non-stationary series are co-integrated, only in that case you can run a regression with non-stationary series. Okay, otherwise never ever run a regression with the non-stationary series.
Sir, one question here. For applying ARDL model, is it necessary to have non-stationary series or stationary? Is it applicable for both, or strictly it is applicable for stationary series?
Generally, generally when you have same level of stationarity, okay, so their non-stationarity also have a level. Okay, so if you have a series stationary, that's referred as I0 series.
Yes.
And if it is a non-stationary series, okay, so it could be I1, it could be I2, it could be I3, it could be IN, but other than 0. If the series is a stationary, then okay, it's referred as I naught series itself. Okay, so with stationary you don't have much of a problem, you can always run. Okay, when you are working with non-stationary series and all of them are having same IN, okay, whether I1, 2, 3, 4, but they are all having the same order of integration, then you go for VAR. Okay, But if you have anything in combination, one series is I1, another is I2, another is I0 as well. Okay, when they are in combination, okay, then okay, you can resort to ARDL. Okay. The problem with the ARDL method, okay, the advantage of the ARDL method is, okay, unlike VAR, which insists on same order of integration, okay, ARDL do not, okay, offer, okay, is not constrained by that, okay, that it has to be same order of integration. You can, okay, have I2 with I1 and I0. Okay, so ARDL does not demand the same order of integration, while VAR, okay, and in that case, okay, the vacuum as well will be demanding the same order of integration itself.
Sorry, sir, but
So,
what is ARDL?
okay, it's a auto-regressive distributed lag model, okay, which is again coming from the co-integration only. Okay, remember I talked about the exception that when you have a non-stationary series, okay, then you can run a if it is co-integrated, then you can run a regression. Okay, so what kind of regression you can run? You can run a vector auto-regression, or you can run auto-regressive distributed lag kind of regression. These are typical formats, okay, in which you can run a regression on non-stationary series. Okay.
What is bar model, sir?
VAR model talks about, again, running a regression with the non-stationary series. So what I've been listing out here in this case is, okay, if you are having all series stationary, you run a regression, there is no problem. Okay, if you are having non-stationary, then what to do? Check whether there is a co-integration. If it is yes, okay, you again run a regression. Okay, if it is not, okay, okay, then what to do in the case? Okay, so probably you must not run a regression. Okay, that's what, otherwise you run into a non, okay, your spurious regression result. Okay? For running a regression between co-integrated series, okay, the regression which is typically being run is your VAR and ARDL. Okay, VAR demands same order of okay, integration. Okay, so that's the demand side. Okay, that has to be same order of okay, non-stationarity. But ARDL are relaxed in that version. Okay, you can have a different order of stationarity. Okay, but there are few, still some author who does not say, okay, that it can go up to I2 or beyond that as well. Okay, so people have reservation on that as well. Okay, but remember the problem with the ARDL model. Okay, so it relaxes that you can have a different order of non-stationarity. Okay, and you can still run a regression, but it's a very less powerful tool. Okay, what does that mean? If something, okay, you can run a okay, on which you can apply a VAR, and you okay, you have determined, or you have applied ARDL itself. Okay, then ARDL, okay, is not advisable. VAR results are more robust as compared to ARDL. Okay, what is power of a test? Okay, if somebody might have heard. Okay, so power of a test, which you say gamma, which is 1 minus beta. Beta is your type 2 error. Okay, if somebody remember, okay, what is a type 1 error and type 2 error? Type 1 error, okay, when your hypothesis, null hypothesis is true and you reject it, that's your type 1 error. Type 2 error is, okay, when your hypothesis is false and you accept it. Okay, so 1 minus that, okay, beta is what is referred as power. Okay, and that power is low with ARDL. Okay, so ARDL is not advisable, okay, if you do have a other alternative. So ARDL, you to keep it as a last resort. If nothing works, okay, then you apply a ARDL. Otherwise, okay, there are better models which have been available to work upon. Okay, but yes, if you have this order of integration is different, okay, then you go for ARDL. Yeah.
Sir,
Any other query?
sir, you have explained in very good manner. Thank you for this informative session. Sir, can we have any book of this material or any written material?
There are so many of them which have been there. Okay, whatever suits your interest, okay, is what you can pick up. Okay, so there are some of these. Kirch Garsner, Lutke Paul, okay. Hill Griffith Lim, okay, that's a basic one, okay, gives you at least an introduction on that itself, okay. But you can pick up these as well. They are typically good text on that. But again, okay, but what is good for me may not necessarily be good for you. Okay, so I like some rigor, some mathematics, manipulations, okay, and okay, but understanding on what is the nature of the estimate itself. Okay, but not everyone might be interested. But yes, these are some typically some of these, okay, which you can refer to. Any other query, any other question to anyone?
So can you tell how to, matlab, an example of co-integration? How can we integrate it through using ARDL?
No, you want an example or you want, okay, how we implement, okay? The example could be many, okay? So, for
It's
example,
basically
okay,
what it is about co-integration is like, as the name suggests, is maybe co-integrating variable, but how can it be done?
integration means, okay, you can say that typical example. You take Sensex and Nifty, okay? Do you think the Sensex continue to go up and Nifty continue to go down persistently over a long period?
No,
Or it may be because
it may like
Well,
depends.
maybe for a day or two, but persistently, can that happen? But Sensex is continuously going upward and Nifty is continuously going down. 10 days, 15 days, 40 days. Can that happen?
No.
Okay. Take gold and gold ETF. Can that happen? That gold is continuously moving upward and ETF values are going downward.
No.
Take another example, okay? You take DVRs, okay? Tata Motors has DVRs. So share price of Tata Motors and DVRs of Tata Motors. That share prices goes up and their differential voting right, okay, shares are going downward. Okay. Or SBI, okay, that's still okay. Here in this case, the logic is more prominent, but you take SBI and you take ICICI. SBI, okay, and with no internal problems to them, okay, that there's no internally a problem with the SBI or ICICI, okay, so they are all been affected by, okay, external shocks. So with the external shock, SBI continues to go up and ICICI continues to go down, okay, 10 days, 15 days, 20 days. Can that happen? Okay, so something bad is happening in Europe or in okay, America, and while the nature of the assets of both SBI and ICICI are the same, equally distributed in Europe and America, so SBI is continuously going upward, but the ICICI bank share prices are going downward. Okay, cannot persistently going opposite to each other. So if there are series from too much from each other consistently and for a longer period of time, the series is said to be co-integrated. Okay. So Sensex is telling you that, okay, there is, okay, the upward movement telling you that the economy is doing good, while the Nifty is telling that an economy is not doing good. It should be going down. Okay. If the underlying is the same, if the economic growth of the country is the same, then Sensex and Nifty should be telling you the same direction, okay, over an extended period. For a short term, okay, it can have some difference in terms of observation, okay, but to correct for that short term as well, okay, we are having that error correction model as well. So if gold and gold ETF prices are different from each other, people will take a long and short position and take an arbitrage profit. So they has to fall in line, and if they fall in line, we call them as co-integrated series. So there are so many co-integrated series. Rather, there is a pairs trading strategy built around the co-integration itself. Okay, so conceptually, co-integration means, okay, the coal prices, okay, probably, okay, I don't know whether you have heard it. Okay, there are 7 types of oil, the crude oil itself. Okay, so there is a Brent crude oil, that's one variety, but then there are other varieties of crude oil as well. Okay, So it's not that, okay, Brent crude oil prices continuously to go up, okay, while other crude oil prices are continuously going downward. That can again cannot happen. So they have to come up, okay, with a combination that they must be falling in line with each other on a long-term basis. In short term, perfectly allowed, okay, but in long term, consistently for okay some extended time span, okay, they cannot move deviate from each other too much. Okay, hence they must be falling in line. That's what is the concept of co-integration. So two series, and that's why I gave you an example of that. Okay, Sensex and Nifty, while illustrating that for the co-integration, and non-stationary series and the co-integrated series itself. And again, I also gave an example for your CPI index and WPI index. So it's not that consistently the WPI is going upward and CPI is going downward. It cannot happen consistently. Yes, 1-2 days, okay, it can happen, but not consistently itself. So there are series which are closely related to each other, and they must not be exhibiting, okay, a different direction consistently. Here, the word consistently is important. So for a prolonged period of time, they cannot give you a different direction. Okay, if they are giving, probably then there is, okay, something, okay, not right in terms of their assessment itself. Okay, so for those series, you can still run a regression despite they individually being a non-stationary series. You can still, I think I've answered most of the questions. If there is any other question, okay, please
So my
go
last
ahead.
question, like last time,
Otherwise, we can wind up
okay,
for the day.
how
Any
can
other question?
Sensex,
Any other doubt? Anyone?
what?
Yes. Sorry, I didn't get you. There was a Clip in your voice.
Are you there, sir?
Okay.
Can you hear me?
Yes, now I'm able to hear you.
I just want to ask, how can a dummy variable be if there is in Sensex and Nifty there is non-stationary, they are non-stationary. How can a dummy variable included it? That how can we know which dummy?
Let's take an example. There's something called as a flash crash. If you have heard of that. Okay. I've heard of flash crash. Okay. Okay. There is, okay, one order which happened in Nifty, which was so much huge an order, okay, that resulted into, okay, Nifty going crash itself. Okay, so all your stop loss order were packed. Once this one big order for, okay, sale of one security was being detected, all stop loss order were executed automatically, and as a result of which Nifty went down while the Sensex was moving upward. Okay, so Sensex was moving upward. The Nifty was, okay, let's take a different color. The Nifty was also going upward, but then there's a flash crash. Okay, and again the Nifty came along after some time, in a day or two. Okay, now this is what has happened. Okay, so two series are co-integrated, but there is a gap in between. If you now see the gap, and if you take a vertical gap, okay, so you will find if you take a vertical gap, the series was moving, and then the gap suddenly was higher, and then it was moving again. Okay? This makes your series non-stationary. If you look at it, remember, by having a shock structural break in your data, that
Yes, sir.
makes your series
Yes, sir.
non-stationary. So now to how to accommodate that? So when your flash crash happened, okay, you include it with a dummy variable that on so and so date of April 2012, their flash crash has happened. Okay, so you include a dummy variable, take that value equal to 1 on that particular day, and before that 0, and after that 0. Okay, so that you are able to adjust it. Okay, make this series, okay, somewhat, okay, in line with that of your the Sensex itself. So you include dummy variable in your, okay, adjustment. So that's again an example where the structural breaks can be incorporated
Thank you so
and
much.
the series becomes again. Yeah, any other question, any other doubt? I hope there are no more questions. Okay, so we can wind up for the day. Thank you, everyone.
Thank you so much
Thank,
for your
thank you, sir.
Thank you, sir. Thank you.
informative class. Thank you so much, sir.
Thank you, sir.
Thank you, sir.
Thank you so much, sir, for such a valuable insight into time series analysis, all these different concepts which really actually at times get overwhelming for a researcher. So with these examples, even for me, and I just speak it on behalf of all the participants, it was very, very useful. Thank you so much, sir. We'll see you again tomorrow.
Thank you, everyone.
Ma'am, can you please share the slides?
We'll ask sir if sir share it, we will share it on the Telegram.
Yes, ma'am, it is requested. Please share these slides.
Sir, will you be able to share the slides?
Sure, I'll send it across. Okay.
Thank you so much.
Thank you, sir.
Good evening to all. Bye-bye. Good night.